Good afternoon, everyone. Hoping everyone can hear me okay. I'm Kate Barter. I'm the co-director of the Sustainability Institute at Ohio State, and it is my honor to welcome everyone to our inaugural Energy Symposium. Over the next 2 afternoons, we have a packed agenda full of terrific speakers focused on topics related to energy transition and decarbonization. We had over 400 people register for today's symposium, many from outside of Ohio State. And I wanted to take just a minute and tell you a little bit about our mission at the Sustainability Institute. In short, SI, as we call ourselves, was launched 2 years ago to provide a coordinating platform for all the ways that Ohio State is working to improve societal well-being while protecting Earth's life support systems. We support teaching, research, outreach, and engagement, and we work to help make our campus itself a more sustainable place to live and to work. We are officially part of the Office of Academic Affairs, and we have over 280 affiliated faculty from 8 of Ohio State's 15 colleges. There is just a wealth of intellectual firepower and passion at Ohio State, focused on better understanding and solving the complex sustainability challenges facing the world today. These challenges range from global climate change to providing access to clean water and nutritious food for a growing global population. And these challenges are often very interrelated. Our institute strives to create opportunities for faculty, staff, and students to generate more knowledge and to bring that knowledge out of the university in ways that can impact the broader communities in which we live. Our institute believes that forming long-lasting partnerships, both within the university community and externally, is a key approach to solving sustainability challenges. For example, we help manage the academic side of Ohio State's partnership with the global energy business, ENGIE, and their partner Axiom Infrastructure. This team was the successful bidder in a private-public partnership to help Ohio State manage our large, complicated energy system on our Columbus campus. Through this partnership, we also have new scholarship resources for students, funding for new professors, support for curriculum development, and other sustainability-related projects. And we are on the path to build a new energy innovation center on our campus. Now, it would come as no surprise to anyone that sustainable energy would be one of the Sustainability Institute's priority research areas. We know that the key to solving global climate change while still protecting economic vitality is a transition to a more sustainable energy system. This leads me to introducing the 2 people really responsible for this symposium, Jeff Bielicki and David Cole. Doctors Bielicki and Cole are our research leaders in sustainable energy and are each a tremendous font of knowledge about this topic. Just a quick note on their respective backgrounds. Jeff Bielicki holds positions in the Glenn College of Public Affairs and the College of Engineering. He also directs the Energy Sustainability Research Laboratory and focuses on topics related to carbon management, renewable energy, and the energy-water nexus. David Cole is an Ohio research scholar and a professor in the School of Earth Sciences. Dr. Cole has tremendous expertise in carbon sequestration, oil and gas systems, and geochemistry. We are fortunate to have professors of such high caliber as both Jeff and Dave at Ohio State. And now I'm going to turn my Zoom podium over to Dr. Bielicki to explain what is next. Thank you.
Well, hello, everybody. It is a pleasure to be here and be able to kick off this symposium. I also have been scrolling through the attendees, and it's also a pleasure to see a number of former students who I've had the opportunity to get to know over my my years here. I'm going to talk today about, can you see my slideshow? No, you can see the presenter view, right? Slideshow. Okay, so I'm going to talk today about, I'm going to give a brief introduction to the symposium and some remarks about what sustainability means in the energy context. Now, why are we doing this? Well, it is clear that we have pushed the atmospheric concentration of greenhouse gases so far outside of its normal natural variability. What I'm showing here is the concentration of carbon dioxide in the atmosphere for the last 800,000 years. We have here at Ohio State the Byrd Polar Institute, which is very much at the forefront at understanding past records of the climate, paleoclimatology, and so on. And it's clear that with this acceleration of greenhouse gases in the atmosphere, there are a number of environmental consequences that we are experiencing and are only going to get worse. Things like sea level rise, increasing temperatures, more extreme droughts, more extreme precipitation events, and so on, have already started and will continue to get worse. And there are economic and social consequences of these environmental effects. Now, there are not a lot of studies that have looked at, well, what do we need to do to have a chance at staving off climate change and these impacts? What I'm showing here is a curve that shows what we need to do in order to have a chance at stabilizing the increase in the global average atmospheric temperature at 2 degrees Celsius above pre-industrial time, so roughly from 1850. Now, 2 degrees Celsius is roughly 3.5 degrees Fahrenheit. And you can see that somewhere beginning pretty soon, we're going to need to start extracting carbon dioxide from the atmosphere while we're still providing energy for our livelihoods and for our economies. And by the end of the century, on net, we will have to be fully extracting carbon dioxide and other greenhouse gases from the atmosphere. Now, this is to have a chance of stabilizing at 2 degrees Celsius above temperatures that are roughly 170 years ago. More recent studies have looked at, well, what do we, if we're going to try and stabilize at 1.5 degrees Celsius, which is roughly 3 degrees Fahrenheit, we got to start extracting carbon dioxide. We got to stop emitting carbon dioxide. We have to slow, halt, and reverse the flow of carbon dioxide and other greenhouse gases into the atmosphere even sooner, within the next couple of decades. Now, in process of this transition, there are a number of things that we need to think about, which I refer to as the sustainability issues around energy. And these will be underlying a lot of what people will be talking about in the next 2 afternoons. We need to continue to improve the efficiency by which we use our resources, not just the energy resources, but also the land resources, the water resources, and other resources. We need to reduce the externalities of how we use these resources, climate change being one of the externalities, water pollution, land degradation, and so on. We also need to increase the availability of energy and the services that it provides, while also increasing the accessibility of it, in levelizing the access and differences in access between rich and poor, for example. While doing all this, we have to make sure that we continue to improve the affordability of energy, the reliability of that energy, so that available, accessible, and affordable energy is there when you want it and need it. And throughout all of this, we have to make sure that we focus on reducing the inequities in the system and having a just transition as we go forward. Now, our symposium here is deliberately organized and with a goal of providing a context for the challenges and the opportunities that we face in this transition that we need to undertake. Our goal is to very much level set the understanding, to provide a fair amount of information around a lot of topics, so we can have a more rich discussion going forward. The symposium over the next 2 afternoons is organized with 3 keynotes. from very esteemed people in the energy and environment space. Interspersed amongst these keynote presentations and remarks are 5 sessions. Each session is 45 minutes long, composed of 3 10-minute talks from Ohio State faculty members on various aspects of energy, of the puzzle that is energy. At the end of these 45-minute sessions, after each of the 3 10-minute talks, we have a 15-minute moderated panel. And so we really encourage you to ask questions in the Q&A portion of Zoom. And you can also upvote questions. If somebody else asks a question and you really like it, you can choose to move that to the top of the list, and we will do what we can to try and address them in the time allotted during these panel discussions. Now, I also want to thank you all for helping us to plan this. We engaged in a number of planning discussions, 4 of them in the fall, 2 in September and 2 in October. The planning discussions were advertised by the Sustainability Institute and elsewhere. So we want to thank those of you who participated in those for helping us think about how we might want to organize this symposium. We also, a number of you submitted some very good questions when you registered. And I think that the way that the symposium is structured, that we'll be addressing in some way about 75 to 80% of those. And I'm going to talk a little bit later about how there's going to be another opportunity for us to address those questions and others that may arise as we go forward. So our first session, our first 45-minute session is really about what it means to go renewable, about electricity as an evolving portfolio, a portfolio of technologies that work together in a system, and how the policy and regulatory environment is one of the contributors to influencing how the electricity system evolves. I mentioned earlier that it is clear that we need to not only stop emissions to the atmosphere, we also need to start extracting them. So we need to go negative. And there are a number of approaches to negative emissions. And we'll have a session talking about that, including some issues with how behavior can be leveraged to help keep that carbon dioxide out of the atmosphere. Now, we can't talk about energy if we ignore people. The people matter, the communities matter, the process by which we go about this matters. Now, this isn't just about putting more wind turbines on the landscape and making sure that the noise or whatever isn't affecting people, or people in the shadow of the turbine aren't getting this flickering. It's also about the fact that in this transition, we are evolving, trying to evolve away from certain types of energy resources. And there's communities that have their livelihoods at stake, and there are identities that matter. We will have a session devoted specifically to the social issues, people, processes, and communities. Now, buildings are a major source of greenhouse gas emissions. What I have here is a little bit of a website from the U.S. Environmental Protection Agency. About this much of the emissions come from buildings. Now, most of us drive cars and we need to get around. We're also going to have a session on transportation, which really I think brings to the fore the need to think about energy and the energy systems, to have a life cycle perspective, both about how much things cost and about what is being emitted. What I'm showing here is an image from a recent article in the New York Times that presented work that came out of MIT Jessica Transick's lab, where you can go in there and you can put in any car that is currently on the market right now, and you can see how much it'll cost, the expected costs over over its lifetime, as well as the expected CO2 emissions over its lifetime. So everything from gasoline to diesel to hybrid to electric vehicles, you can put it in there. At the end of tomorrow, just before we wrap up, we're going to talk about what are we doing here at Ohio State. Now, we've got a lot of things going on. One of them is a National Science Foundation National Research Traineeship, the empowerment program that is training PhD students in a variety of co-curricular activities and curricular exposure to broaden their awareness beyond the discipline in which they are getting their PhD. So for example, engineers are being exposed to the social science and issues therein with energy and energy transitions. A little under a year ago, Ohio State released its climate action plan. Part of that plan seeks to reduce carbon dioxide emissions by more than half by 2030. We're going to have a discussion about that, as well as a conversation or a presentation by those involved in the Ohio State Energy Partnership, as Kate mentioned. I mentioned earlier that this will not be the end. We will have the opportunity to have a second, use you to cover things that we haven't necessarily dug into as deeply over these 2 days. We're gonna have 3 events in April where the topics and the participants and the format, we're still working on that. And what we need is your help in what you'd like to see. So things such as what we might have glossed over, what we might have not covered as well as you wanted, as well as things that you'd like more information on. You're going to have a survey to fill out after we're done, and we're really going to take that feedback seriously. And I should also mention that we do have live captioning available, so please be sure to take advantage of that as you need to. And I mentioned earlier that we have these 3 keynotes just before the session on what are we doing here at Ohio State. We're going to have Michael Weber, a professor at UT Austin, as well as the Chief Technology Officer for ENGIE, our partner in the energy management here at OSU's campus. Kicking off tomorrow will be Scott Tinker, who among a variety of things has produced 2 documentaries, Switch and Switch On, which is really about the needed energy transition. And coming up next, we have Rob Socolow, Professor Emeritus at Princeton University, who over his decades of very thorough and rigorous engagement with all things energy and environment has introduced a number of frameworks for how to think about the challenges and the opportunities, including stabilization wedges, 1 billion high emitters, committed emissions, and more recently, these destiny studies. So with that, I would love to introduce Rob Socolow from Princeton. Is Rob available? Rob, there you are, Rob. Rob, as I mentioned, is a professor emeritus at Princeton University. And what he's going to talk about is some of the challenges and pitfalls in evolving our energy system. And what we're going to do is we're actually going to have a panel discussion interspersed throughout Rob's remarks with 2 of our newer faculty members here at Ohio State, Daniel Gingrich, who has a joint appointment in the Departments of Civil, Environmental, and Geodetic Engineering and in Integrated Systems Engineering, and Jeffrey Jaquette, who is also an assistant professor, and he's in the School of Environment and Natural Resources, and he's a rural sociologist. So with that, Rob, the floor is yours.
Thank you. Thank you very much. It is an honor to be invited to give the opening keynote in a marvelous symposium. I know Jeff from quite a while back. He has amazing leadership skills, and they're in clear view here. I'm going to share my slides, and then I will come back and you'll see me again, but this is how it works, I guess. To make sure that works. Get over there. Okay, so the title you've heard, Symposium is here, the panelists are listed, and let's get going. So the poster child of climate change is a figure that I am still imagine many of you have not seen in the audience, and many of you have seen it too many times. It's an amazing data series from of the carbon dioxide concentration in the atmosphere. It's measured in parts per million, which means what fraction of the million molecules of air, each million molecules of air that you breathe are carbon dioxide molecules. The answer right now is about 415. When I started working in this field, it was about 330, 325. It's almost 100 higher. And this blue line at the bottom is what it used to be, 280 parts per million for many, many, many years, up to about 1800 when the Industrial Revolution began. Still, almost all of that increase has been in the last 50 years or so. Also marked on this slide, 2050, which isn't that far off to the right. This curve has been rising relentlessly. Will it eventually level off and even come down? It's up to us because, well, let me first show you. This is where those data come from, high up on Mauna Loa, one of the two large volcanoes on the big island of Hawaii, mostly isolated from industrial sources. I'm at the left there with Peter Tans, who's now taking care of the carbon dioxide network of the world through a base in Colorado. And if you look closely between our shoulders, you see the very curve I showed you. This is lava-based research station up a long road. If you take that graph and say, well, why do I think this has anything to do with fossil fuels? Starting quite arbitrarily at 1995, I drew this dotted line, which would mean the blue line, which would mean how much would carbon dioxide concentrations rise over 25 years if all the carbon dioxide emitted from fossil fuels remained. And it turns out that's about twice as much as actually remains in the atmosphere. It's not 1/10 as much, in which case we would know that fossil fuels were unimportant. It's actually twice as much. And why isn't it exactly equal? Because the land is absorbing carbon dioxide and the trees and the leaves. As more carbon dioxide is in the atmosphere, things grow better. And the oceans are dissolving CO2 at the surface of the ocean, making the ocean more acidic. And thanks to those two sources, we see about half of the impact of fossil fuels. But we see it, and we see it big time. Why do we care whether the carbon dioxide concentration goes up? So what? Well, there's pretty good understanding of how the planet works. Carbon dioxide prevents the Earth from cooling off to outer space. The more of it there is, the more difficult it is to get ourselves cooled off, to balance the sunlight that comes in. And so the equilibrium temperature rises. About 1 degree Celsius already. Lots of people are talking about the target of 2 degrees. And I put on this graph 3 degrees and roughly a linear scale. It's not fully linear. That about 1,600 billion tons of carbon dioxide will raise the temperature, added to the atmosphere, will raise the temperature of the surface of the planet about 1 degree Celsius, so that you might have this. We've got 1 degree Celsius already. Another degree is what we're talking about, maximum emissions, and we may well be heading for more than that. We don't know this science perfectly. We are gradually learning how the Earth works. It's a complicated place. Give a sense of the uncertainty in the science. If we aim for a 2 degree world, we could end up with a 3 degree world, which would be being unlucky at about 1 chance in 6. And if we aim for a 2 degree world, if we aim for a 3 degree world, we could end up with a 2 degree world being lucky. And again, 1 chance in 6. All these temperatures are Celsius temperatures. Uncertainty motivates more action, not less, because uncertainty means there's some very bad outcomes that we can't rule out. We are risk averse. We should care more about avoiding bad outcomes than the pleasure of having a better outcome than we expected. So this graph gives you a sense of what 2 degree scenario really requires. We have the carbon dioxide concentration. I said before, 1,600 billion tons of carbon dioxide added to the atmosphere will raise the temperature about 1 degree Celsius. That 2 triangles there each are 1,600 tons of carbon dioxide. 80 years times 40 at the top and a half for the area of a triangle gives you those numbers. And the 2 degree scenario, since we've already got 1 degree, can be thought of as going down at the same rate as we went up. We climbed over about 80 years to today's emissions, about 40 billion tons of carbon dioxide per year now. Come down the other side, 80 years is to 2100, halfway is 2060. And the world, this is not the US, the world would have to emit about half as much carbon dioxide in 50 years, 40 years here as today. That gets you down to 20 billion tons of carbon dioxide. We have about 5% of the world population. So our share would be about 1 ton of carbon dioxide, 1 billion tons of carbon dioxide per year. That's down from 5 right now. This is what that says, 5% of the world's population. Our quota would be about 1 billion tons of carbon dioxide emissions in the US in 40 years. Various scenarios put it lower than that because we need to leave room for other countries. But basically, our emissions down by 80% means a completely different use of energy and fossil fuels, for the most part, being left in the ground, although I'll show you some exceptions. It's a very, very difficult and unfamiliar task. We're talking about the whole world, and many people begin by saying, come on, the developing countries have so many poor people, indeed they do, and they're using energy in very unhealthy ways. The graph at the left shows you that there's almost as much mortality in the world from the smoke of indoors from burning fuel, typically not very good fuel, coal briquettes or biomass, dung perhaps, about over 1 million deaths a year, comparable to the deaths from malaria, tuberculosis, and AIDS. That doesn't have to happen. Step one is to build a better stove and venting system. That's what's going on for this woman who's rather pleased with the life she's got relative to what her neighbors might have with an unvented stove. But step 2 is a petroleum-based fuel, which will indeed put extra CO2 in the atmosphere, but may alleviate improve her life very substantially. So I always argue, don't start solving climate change on the backs of the very poorest. But then there's a step 3 in which that fossil fuel will again disappear, and there will be an electricity-based cooker that will take that place. So we have all these steps ahead of us, and in a fairly large hurry. There are about 3 billion people cooking on what are called unconventional fuels, and they're going into a modern age. So we have to deal with the world's poor at the same time as we're dealing with our own relative prosperity. If we're going to limit ourselves globally to emitting something like 1,600 billion tons of CO2 altogether, maybe even less in the next 80 years, that's a completely unfamiliar concept of a budget. When will we emit it? It doesn't really matter if we emit it in 2070 or 2030 in terms of the atmosphere, because much of the CO2 stays there for hundreds of years. So it's now versus somewhat later. It's whose carbon dioxide, whose fossil fuels. We have countries like the Middle East completely dependent on fossil energy production, regions of the US in the same way. Used where, who gets to use it? Fossil energy travels a long distance. For what purpose? Are we going to focus on the needs for, say, petroleum for cooking in the developing world? And which fossil fuels, coal versus gas? I know Ohio is a coal-based state, losing its coal industry in favor of natural gas. From a greenhouse problem, that's actually good news, because coal puts about twice as much carbon dioxide into the atmosphere as natural gas does when they produce electricity. And why is that? It's because the hydrogen rides along with the carbon in both coal and in natural gas. In natural gas, there's 4 hydrogen atoms for each carbon atom. In coal, there's about 1 hydrogen atom for each carbon atom. The hydrogen gives you water with energy. The carbon gives you carbon dioxide with energy. So you have a more climate-friendly electricity source in natural gas because you get that extra energy without carbon from the hydrogen. But we have this completely new problem. I want to relate this to everybody in this audience who has their individual emissions. We told this about carbon diaries, individual carbon budgets. And why do I start with 5 billion tons of carbon dioxide a year as a reference? 5 tons of carbon dioxide a year, excuse me. It's because if we go back to that 40 billion tons for the globe and say there are about 8 billion, almost 8 billion people, the world's individual per capita share is 5 tons per year. The US is about 3 times that. The US per capita is about 15. India might be 2 or 3. China and Europe are around 10. An individual American is about 5. What about you? 30,000 kilometers a year of driving or 20,000 miles and a 45 mile a gallon car will give you about your whole quota, your whole 5. flying about the same distance as driving for 20,000 miles of driving, of flying in an average airplane will give you your full quota. Heating a home in Ohio with natural gas will get you about the same full quota. Each of these gives you the full amount. And for the electricity, your computers, your lighting, your air conditioning, you'll use it up with about 400 kilowatt hours a month, which is not much for per capita. It's lower than that, it's lower than what many of you are using, but quite tolerable. If it's coal-based and if it's gas-based, it's about twice as much. So you go back and look at your electric bills and see where that comes out. Princeton did a study and uses about 9 tons of carbon dioxide, emits about 9 tons of carbon dioxide per capita for about 10,000 people who are combinations of students and staff. Jeff and I looked at the Ohio State numbers, more like 100,000 people and not quite 10 times as much energy, maybe more like 2/3 per capita. You're obviously using energy better. And since it's electricity based on coal, it's an even bigger difference. So you congratulate you on doing your carbon accounting and then your carbon investments to bring the campus energy down. I want to turn now to some brand new results. I've never shown them on slides before. I developed them for here. An interim report by a group I'm associated with. I'm not in any way a core member of it, but I've got my name on the papers and I've endorsed the work on Net Zero America, being done at Princeton over the last 12 months or so. Very detailed computer modeling of how different a world it would look like in 2050. We had closed down most of the fossil fuels and put substitute energy in there graphically, and you'll see my first group. I've got 4 maps to show you. First one is, where are we starting from? There are 7,500 facilities in the United States, heavy industry, power plants, and oil and gas facilities, which individually are giving more than 25,000 tons of CO2 per year. A coal power plant, the big one, will give you about 6 million tons. This is much smaller than that, but large enough to be interesting. 7,500 of those, adding up to about 60% of the total global emissions, from the country. The rest are things like cars and small buildings. That's the other 40%. And they're all over the country, and they're all kinds of facilities, and every last one of them will be a target for Net Zero America. Solar and wind would, in the view of this particular project, come on very big time. 3 million megawatts of wind and solar, about half each, spread around the country. Wind concentrated somewhat to the west of you, but including lots of wind in Ohio. Solar mostly in the southeast and in the west, but some of it in Ohio. Project by project, needing to be permitted, endorsed by the local community, and gradually shifting the grid over, having storage in place to handle the intermittency of wind. A major transformation of the energy system, which I'll say more in a few minutes. Specific interesting development is carbon dioxide infrastructure, pipelines to move carbon dioxide around. You may not have heard of many of them. There isn't anything really near you for that purpose, but they are all over the country. Already we have 8,500 kilometers, about 6,000 miles of carbon dioxide pipelines. They're mostly associated with the oil industry. They move CO2 from one location to another in different parts of the country, but nothing like what we're heading for, which would be 10 times as many miles of CO2 pipelines, coming at a large amount of collection of CO2 from agricultural products that become, or dedicated grasses that become energy, and carbon dioxide is captured. That's what all the green dots are. And in other ways, bring a lot of carbon dioxide around the country. Some of that is the negative emissions that Jeff was talking about. And we are often running with something we have not even begun to think about, a national carbon dioxide grid. You're going to hear about it over the next year or two as the Biden administration starts putting in place the kinds of investments that will have the potential to bring about a net zero America. It's an amazing vision. We haven't begun to digest it. This is one of the ways of thinking about it, something we've never heard of, practically running all through the country. And that's by no means a unique answer to what it might look like. There are other answers that one could argue for as well. But you see Ohio growing crops, burning them for energy or hydrogen, putting the carbon dioxide in the pipeline that might go all the way down to Texas. We haven't built any of that. Pipeline construction needs lots of community approval, does create a lot of jobs. Is this part of our future or isn't it? So looking back on an infrastructure we built in the 1950s, 60s, and 70s called the US highway system, it's a pretty intricate infrastructure too. Could we build that today? Do we have the willpower, the capacity to work together across parts of the country, across parties, to build something like the national highway system? The question we are confronting really is very similar to that question. Brand new infrastructures, visions, decades of development, and essential if we are going to deal with the climate problem, which we wish weren't there. Nobody thinks it's a great thing. It's limiting what we can do on this planet, and we've got to be clever to work around some of its severe constraints. So let me summarize what I've tried to tell you so far, and then we'll take a move to a panel. I've said, first of all, that fossil fuel use is the dominant reason for the increase in atmospheric concentrations of carbon dioxide. The climate science cannot yet tell us how quickly the climate will change a given concentration trajectory. And uncertainty motivates rather than demotivates action, because very fast change cannot be ruled out. I've got 6 altogether. The global goal of restricting the rise in global temperature to well below 2 degrees Celsius requires roughly at least having global CO2 emissions at mid-century. And the consequent US share by population would be 1 billion tons of CO2 per year. And if we take things seriously, maybe less than that, it's down by a factor of 5 from where we are now. CO2 emissions today are, think about that, cars, planes, house heating. Carbon dioxide emissions today are the combined result of ordinary human activities and the fossil fuel-based energy system. There are no, as Pogo says, we met the enemy and it is us. We are actually responsible for these emissions. And a swap of nearly the entire current fossil energy system for another system, a low carbon one over just a few decades is the assignment, and it's a global assignment. So you're meeting for 2 days to look at a very, very severe problem, and one that will challenge the young people in this room over their entire lifetimes. It's not going to go away. It's not a myth, and it's not the slightest bit simple to deal with. So I want to go to the panel now, Jeff. We can and pretty much pass it to our 2 friends, Daniel and Jeff Ree. I'm going to ask them, what does this all mean for Ohio in your terms? You may want to frame it slightly differently, but that's what I'd sort of like to hear. Bring it down to earth as much as we can.
Yeah, so I'm going to go first on answering that question, and I'm actually going to see if I can share my screen because I have some maps that I want to show off to put this in context for Ohio and what our energy resources look like. So this is a map of Ohio using information from the Energy Information Administration. And what it's showing is where the coal-fired power plants are located in Ohio. That's those black circles. And also there's this shaded black area, which represents where coal resources are located in the state and where we see activity from coal mining and coal processing. And what you can see from a map that looks like this is that the geography of Ohio's coal resources are very concentrated on the eastern side of the state, kind of in the Appalachian Mountain region. And if you were to look at a similar map like this for natural gas, we see a similar trend. Again, here, the blue circles represent natural gas plants in the state of Ohio, and the light blue shaded areas represent areas where we have oil or natural gas extraction wells. And again, we see that the natural gas extraction activity in the state is concentrated on the eastern side of the state. But if we think about this for the renewable resources, and in this case for wind and solar, that's what this map is showing us here, is we've got our solar PV generation facilities in the yellow circles, and we have wind turbine farms shown in the gray circles, is that they're much more concentrated on the western side of the state. So there's this fundamental difference that we have between where we have our resources located. And if we think about where we might build some of these future technologies, in particular thinking about wind, we're going to see this trend continue. This is a map from the National Renewable Energy Laboratory, which is the national lab here in the United States that focuses on renewable energy resources and generation. And it's showing roughly the potential for building wind resources and the amount of space in each of these shaded squares that could produce competitive, potentially wind generation. And what you see here is, again, on the western side of the state, it's pretty dark because there's a lot more potential to build wind turbines there because the wind tends to move faster there. Whereas on the right side of the state, or the eastern side of the state, we have lower potential because there's just not as much wind resources. And so if we were to compare these maps side by side, like I've got here on these two screens, we can see that there is this fundamental mismatch that we're going to need to grapple with in Ohio when it comes to thinking about all of these fossil energy resources that we have and we've built up, and we have communities that are used to being able to use and extract and get a livelihood from using these resources, versus those on the eastern side of the state, the western side of the state, where we have the potential to build wind and solar turbines, but a much higher potential and much more economically competitive. And so with that, I'm going to toss this over to Jeffrey to talk a little bit more about the social implications of this for the state of Ohio and the people that live here when it comes to this transition away from potentially fossil fuel energy resources.
Thanks, Daniel. So certainly true that we have a monumental task in front of us. And I think that, this switch to renewables in Ohio is having and will have, some pretty tremendous impacts to the people that live there. Just, thinking about those coal communities, a number of the coal-fired power plants that Daniel just showed are actually no longer there. Just even in recent years, a number of those have retired. Taking with them some of the largest, sources of employment for a lot of communities. There's a lot of coal mines in Ohio that have recently closed or are on the verge of closing. And, I think from a carbon standpoint, people would agree that this is a good thing. But again, these are lost jobs. These are sort of, sources of sort of community identity that have stood the test of time for, hundreds of years now. And you might say that, and it's true that, employment in the coal industry has been declining since the 1920s or 1930s. And that, this is a fraction of the employment base in these parts, and that's true, but it's also true that, these are some of the biggest sources of employment in the area. And we've seen an increase in jobs related to natural gas, but the jobs aren't really analogous. They're different industries. Natural gas tends to be more regional, tends to be more sort of transient in nature, whereas coal obviously is sort of situated in place. And then on the flip side, thinking about renewables, if you talk to a lot of renewable energy companies, as I have, they will tell you sort of the biggest problem that they face is community acceptance of the renewable sort of facilities. And that includes, wind and solar, and that we're seeing real resistance to these types of developments in Ohio, but also sort of in other places across the country. And, the wind resource map in Ohio, some of the bluest parts of that already have wind farms there. And so we might be asking these communities to sort of double down on the number of wind turbines that they have. And sort of the challenge there is to do that in a way that is sort of just and equitable to the people that live there, and to make sure that they're not being held harmed by this development, to make sure that the costs and benefits are sort of equally distributed across those communities, but also sort of across the state. And so to make sure that, we in Columbus aren't the ones benefiting, whereas these other places are the ones sort of, being harmed by this process. And so, and I think, there's sort of like the social economic impacts, and then there's sort of like the social economic barriers to this sort of transformation. And I would encourage us to sort of think of those as similar, in that if we solve sort of the impact problem, we'll probably solve, the sort of the barriers or the resistance from the people that live there also. And I guess maybe with that, we can turn it back over to Rob to continue the keynote.
Hey, what I have to do here. Okay, so I'm on screen, right? And I will again share my screen. Very glad for that discussion, and hope I'm in the right place now. Yes. All right. Okay. So is my full, okay. Is that on screen now, Jeff? We're in business? Okay. So we'll talk about this swap for the rest of the slides. We'll come back to a panel, but look, the conversation about Ohio is exactly what we need to have all over the country and the world. It does come down. I didn't know the microgeography of Ohio. I'm very glad to know it now. It's the microcosm of having severe impacts in Texas, Oklahoma, and Louisiana, but benefits in Iowa and Nebraska and Kansas. I mean, we're getting movements in from left half, east half to the right half of the state because there are these major differences. And the same thing goes for Saudi Arabia on the one hand, and some very windy country somewhere. So it does come down to public acceptance. I want to talk about the swap then, which is, and talk only about the energy system for now, and not even the energy demand system, which is very, very important, but just the sources. And we have three broad categories of low carbon electricity and energy sources. Those that come from the sun, which come in at least 4 versions: solar, wind, falling water, which is hydropower, and things that grow. Fossil fuels, this is really important. We don't have to give up fossil fuels if when we burn them, we capture the carbon dioxide instead of letting it go to the atmosphere. It's 2 separate decisions: to burn the carbon dioxide for energy and where the carbon dioxide waste product goes. The atmosphere has been our waste basket, but it doesn't have to be. We can capture that carbon dioxide in the smokestack and put it underground, for example. Then there's the nuclear options. Fission now, fusion maybe someday. People working on it at Princeton's been a center for that research. I don't think it's in the next 40 years, but it might be in the latter part of the century. Fission is definitely there, has major issues. We have an industry that at the moment is dying out in this country, but not in others. So what about them? The way I want to think about all of this is with the word conditionality. Conditionality means we will, and it's a question for each one of you individually. What would have to happen to the world while it solved climate change that would make you comfortable that it had been better than not doing it at all? The more you think climate change is dangerous, the more forgiving you're going to be about the downsides of options. But all in all, someone would say, for example, if the world is not more equal, if across countries and within countries, while we save climate change, I don't want anything to do with it. You're hearing that from some segments of America. Others might say, if it's going to make biodiversity worse, that we lose lots of species, I won't consider it a success. Some of these arguments will be from the natural, environmental, if you like, and others social. What must happen, what must not happen? I would claim that all the arguments about climate change mitigation today, except those that say there's no problem at all, are arguments about conditionality. What are we willing to live with? So let me give an example of conditionality. Suppose you're a forester or an agronomist in a world where the carbon price is very high, and you're told that carbon dioxide storage in your forest or grassland is your only goal. What would you do? You might grow a single species, which would reduce the biodiversity. You might pour on fertilizer, not caring that the carbon dioxide was emitted making the fertilizer somewhere. You might evict an indigenous population. Be inventive. Now, change roles. You're the policymaker watching that other person making decisions about her forest. What conditionalities would you place on the carbon market for biostocks in the interest of eliciting actions from that forester that you would welcome? Because people will meet the rules. They'll satisfy the rules, and often not more than satisfy the rules. So writing up the rules, thinking through what we need to know to write up the rules is the heart of this problem. With solar power, how much land impact are we willing to tolerate for solar power? How many parks out that you got used to biking through are you willing to see, which are open fields, let's say, turning into solar fields? Solar comes in 3 versions. One, these are very large plants in deserts. You've got no desert in Ohio, but you might not have anything as big as anything to the left there. Other parts of the country will. You have the rooftop solar. Definitely, how fast is that growing in Ohio? It's not the best place to collect solar energy, but it can, that number of panels is presumably taking care of that roof and then some. And then you have solar helping the poor in very local places. There's a single panel attached to a house out in perhaps Mongolia. I'm not sure exactly where that picture is from. Comes in all those versions. It's unbelievably interesting now that the price has dropped so dramatically, 100-fold from 1,000-fold from the space stations, 10-fold in the last 10 or 20 years. It's so inexpensive that all the costs now are putting it up, getting its permits, putting it onto a mount, keeping it clean, and they're being built in gigantic quantities. How welcoming will Ohio be for these things? The conditionalities about land impacts, I think, first of all, but also reliability, which it shares with wind. And I want to show you one kind of interesting, I think interesting piece of work that I did with a colleague, Pedro Haro. We looked at Texas hourly wind data for a year. And we asked, let's pick an arbitrary threshold, which is half the average of the year. And every time the output dropped below that number, half, 3,000 megawatts of wind power, this all the wind of Texas power production. Start counting and then stop counting as soon as the wind has risen above that value. And the 4 longest intervals where it was less than half of the average for hour by hour were 3 of them were 2 days long, one was 4 days long. That's a lot of lost wind when you're trying to run a factory, for example, or you want reliable power. That implies real challenges to storage, which is day scale, not hour scale. Here's that particular 43-hour interval, where the power dropped. So how are we going to deal with wind? Gas and wind packages and gas and solar packages are very attractive because the gas turbine can turn on and off. It's a jet engine. Jet engines have amazing history in your state with a museum that I still remember over in Akron. And so we're going to have a major challenge accommodating solar power and wind power because of this intermittency. One of the things I wonder about is whether our behavior patterns will change from what we're used to now. The power engineer today has an assumption that he or she must provide power whenever anybody wants it, no matter what's happening outside. Obligation to serve amounts to that. Suppose we actually get more relaxed about doing things a little differently when there's a string of low wind days or cloudy days, and we actually maybe we take a factory and retire it and reduce some of its output. Maybe we're used to working from home these days. Maybe we do some other things in the workforce. The snow day in schools is an example of that. We don't get too upset about not being able to bring children to school every single day. A few days in winter, okay, we can't, and we accommodate. Might we be dealing with more of that so that the power engineer would have a slightly different assignment? The wind power is extremely interesting. It's just in that 3,000 megawatts of wind I showed you before the break, before the panel, was half wind and half solar for the US, about 1.5 million megawatts of each. One of the places it's going to go is off the 2 coasts of the US, particularly off the East Coast where it doesn't get as deep as quickly. This is the oil industry marching into deeper and deeper water in roughly the period from 1975 to 2000, even further depths since then. Think of that kind of evolution for offshore wind as well, and a transfer of technology from the oil and gas world, which knows how to build floating platforms tethered to the ground, to the wind industry. This is already happening, but imagine a major role for the wind industry in partnership with the oil and gas industry. It's just possible. One of my favorite low carbon technologies is taking a coal or natural gas power plant, burning the fossil fuel, capturing the CO2, keeping the fossil energy industries around, putting the carbon dioxide directly below the oil, below the plant, as in this picture, or piping it 100 or so miles away. You go west from Ohio, you get to the Mount Simon Aquifer in western Indiana and in Illinois, And you might have pipelines of CO2 taking it there and then go below ground into porous formations of the kind that hold oil and gas, but in this particular case, typically don't hold oil and gas. That's a picture from a Scientific American article in 2005 that I wrote, and that's a joint effort of lots of people, that picture, to imagine a coal plant with the CO2 capture. But Mountaineer, not very far from you on the West Virginia side of the Ohio River, was a project of this sort also about 10 years ago. So in addition, so this is a very simplified abstraction of three ways of not having the current carbon economy. The center top, you have the way we're powering the economy today. We're taking, these are carbon flows. Take carbon out of the ground as fossil fuels, coal, oil, and gas, run something like a car or an engine, a turbine, and the carbon dioxide goes to the atmosphere. All fine, wonderful fuels, except the atmosphere isn't as big as we would like, and we're changing it at you saw about 40% more carbon dioxide in it now than 100 years ago. Changing the planet's climate, we just can't do it. We wish we could, but our planet is too small. Fossil carbon dioxide capture and storage, that's what CCS stands for, is off to the left, where you take the CO2 you take the carbon out of the ground, but you put it back in the ground. Take it out as a hydrocarbon, put it down as carbon dioxide. That's a closed system. Carbon is coming out as it does right now, but where it goes is entirely different. There's carbon dioxide in the air. Many people have become interested now in getting that carbon dioxide, which is only 400 parts out of a million, pretty dilute, grabbing it anyway, perhaps making a fuel from it, driving a car with it, and then putting it below ground, or growing a plant. A plant is growing and taking it out of the ground for us. Then we burn it and we capture the carbon dioxide. If we do that, we're scrubbing the carbon dioxide out of the atmosphere. It's going down. That's what net negative carbon is that Jeff had on his slide when he was introducing this symposium. And finally, on the third side is air capture. One second. Air capture and use, where we actually we don't get greedy and put the CO2 below ground. We take CO2 out of the air, make a fuel, and burn it again. Then we are not adding or subtracting CO2 from the atmosphere. I think that's a helpful way of thinking about it, particularly the first two on the left are being widely discussed today as the backbone of the carbon part of a very low carbon future. There is also the non-carbon part, which is wind and solar and nuclear. So let me turn to nuclear. The slide on the left, the graph on the left tells you something I think some of you know, which is you can't turn a nuclear power plant off completely. You can't put the fire out that is there. After one day, about 1% of the output is still being produced right there. It's not like a campfire that you can pour water on and you know it's safe and you can go back and go on a hike and no forest fire is gonna start. In this case, the reason is that the fission event that created the heat for the power plant also made fission products like a whole bunch of different fission products with their own half-lives that are sitting there and decaying in a minute, in an hour, in a day, adding to the energy production, the last tail of it, which is still 1% is 30 megawatts at a typical large nuclear power plant. You've got to remove that heat or it gets very hot there. It starts fires there. It melts metal there. The picture of 2 Mile Island, not far to the east of you, was exactly that kind of incident where the power plant did not have the mechanism of getting water onto the fuel rods that were producing heat. You melted right through a whole lot of metal. So we can't build that. We have to deal with safety issues that are going to frighten people and are in the way of building nuclear power plants that are competitive today. Maybe we'll get past that, but I think the conditionalities, they've got to be very safe. And then they also can't encourage wet nuclear war. There are a lot of countries that want nuclear weapons today. Of course, to prevent nuclear war with their neighbor, they would say, but they make it more likely than if they didn't have the weapons at all. And the nuclear power system, in two different ways, encourages nuclear weapons. One is that the uranium is enriched in its rare isotope U-235 on the way to the reactor in special enrichment facilities. And if you tune those enrichment facilities just a little different, you can make weapons grade uranium. That's what Iran's argument is about. We got them to agree not to make nuclear grade, weapons grade uranium, but only power grade uranium. And then we walked away from the agreement, and now they're going back towards something closer to weapons uranium. They can go back to first, but it's a temptation always. And then the plutonium, which is made in the reactor, can also be a nuclear weapons material. And we've got to be very, very careful with how that plutonium is governed when this fuel comes out of the reactor. Just a little, and so in summary, every solution to climate change is dangerous. We should start with that assumption. I've mentioned some of them here. I didn't mention geoengineering, which is on people's list for how to manage climate change, which is to modify the planet in a different way. Who's going to make those kinds of decisions? I call it technological hegemony. And in addition to the kinds of impacts that are on the technical side, there are impacts on local communities, on equities. We heard in the first panel, they're absolutely central. So we must address the conditionalities that make a solution unacceptable to the point where it becomes acceptable. If we make too many conditions, we can't deal with the problem at all. Hippocrates has the last word. The Hippocratic Oath says, do no harm. And I love this quote. I will apply for the benefit of the sick, says a doctor, all measures that are required, avoiding those twin traps of overtreatment and therapeutic nihilism. Overtreatment brings about a severe reaction to the drug. Therapeutic nihilism means never using the drug. Well, I have a final slide that is for the young people here. The world has a terribly inefficient energy system, and the cost of solar power, wind power have fallen precipitously, and most of the physical plant is not yet built around the world. So there's lots to do, and for all of us, not as young as the young people who have this challenge upon them for their whole lives, very smart young people now find climate and energy problems exciting. I'm told that Jeff got 400 people signing up for this symposium. That's a pretty good number. And so let me go back to the panel and the Q&A and pass it back to Jeff. Thank you very much.
Great, thanks, Rob. Daniel, Jeffrey, thoughts, comments?
Yeah, so I think for this one, Jeffrey and I wanted to build off and talk a little bit about that last point on Rob's last slide, thinking about how young people find climate change and energy problems exciting, and talk a little bit about opportunities they have here at Ohio State to help contribute to solutions to climate change. And so there's a lot of research that takes place here at Ohio State on every aspect of the energy sector, from developing and studying new fuels to working on the batteries that we're going to need for energy storage, developing and testing out new designs for solar panel materials, working to develop carbon capture and sequestration systems that we can implement at scale power plants, all the way up to thinking about policies and economics of climate change and the energy system in the future. And so there are many opportunities for undergraduates, especially, I know, speaking personally as someone in the STEM fields, for STEM undergraduates to get involved in undergraduate research. So as the undergrads in attendance today listen to some of the talks and some of the faculty, I'd encourage them to see if there's ones that resonate with them, or if there's problems they want to find out and learn more about and contribute to. And then reach out to those faculty or reach out to other professors in your department and see if they have research going on that you can contribute to and take part in, so that you can also be part of the solution to this big problem that we have. There are other opportunities too, not just for STEM students to get involved. So for instance, the Sustainability Institute has a series of small grants of about a $5,000 max that undergraduates and graduate students can apply to in order to do research and or find ways to use Ohio State's campus as a living lab. And so those opportunities are also out there for you all to pursue and get involved and get engaged in. So I wanted to flag those for everyone in attendance today to make sure they knew about them, so that they can get involved and get engaged and get excited after today and tomorrow's talks. With that, I'm gonna pass it off to Jeffrey.
Thanks, Daniel. Jeff, I guess let me know if we want to go to questions. We have a lot of really great questions in the chat. But just a couple of more like causes for optimism, as was the task for the second part of the panel discussion. I think even in my 4.5 years at OSU, I think the approach to energy and sort of like the role, the thinking about energy has changed quite a bit, I feel like, in recent time with the arrival of NG, the beginning of the Sustainability Institute, just a number of new research projects, new sort of institutions on campus, the Empowerment NRT program, which will be highlighted later in the symposium, the interdisciplinary graduate program, a number of really great research programs that are beginning on campus or have been, ongoing on campus, including the Infuse project that I know Jeff is involved with to look at, the nexus of food, energy, and water systems. There's a lot of different projects on campus, and I think a lot of cause for optimism. And I think as Dr. Socolow had mentioned, there's a lot of room for growth here. So the nice thing about the way we've been doing things up until now is there's a lot of room for improvement, and I think we're going to hopefully see that improvement soon. Looking at the time, Jeff, I guess I'll turn it back over to you for any questions for our keynote.
Yeah, great. Thanks, Daniel, Jeffrey, and Rob. One quick note. I'm told that, so I have answered all of the questions that have appeared in the Q&A, but I'm told that is not showing up. So to me, they show all resolved. So one question, if you have asked a question, do you see my answer? Because I'm aware that nobody else apparently is seeing the answers, and behind the scenes, they're working on fixing this. There are a few questions that I want to highlight that are really good. Well, all of them are really good. There's a few that are rising up. One is about materials demand for wind and solar and so on. And if we are really going to build this out, don't we have issues with the demand for materials and how we get those materials? Cobalt, lithium, name your metal.
I don't know a lot about this. The wind turbine blade is like a canoe blade so far. Combination of wood and hydrocarbons of Kevlar. It's built to be light and strong. I'm sure there are materials that will come along that were different from that. There are some unusual materials in the photovoltaic panel that have electro-optical properties. One of the questions, Jeff, that's implied by this, which is really interesting, is this end of life of panels and wind turbine blades. You get one number if you assume everything's thrown away, and you get a very different number if you have an efficient recycle system. The lead acid battery is an example of a system that initially all of it was dumped in the woods and with lots of lead going into the environment, although not very fast. And then companies realizing that they could take the lead, smelt it down again, and put what's called secondary lead. And there's a very high effective recycle system for the lead acid battery, not so much for the nickel or the lithium battery yet. So the materials demands are going to depend a lot on what's called the industrial ecology of the system. And it's going to be very important. The next step for engineers is design for recycle. If you think about the fact that it's going to be recycled, you might use somewhat different materials or separate them in some way. So the subject is really rich. It's again, as Jeffrey was saying just a moment ago, wide open.
Great. Another issue that people have brought up is when we burn natural gas, we get roughly half the CO2 emissions than when we burn coal, but we have leaks throughout the system and the infrastructure, the pipelines, and so on. How do we think about that? How do we address that? This is open to anybody.
Jeff, what do you mean? I'm not getting. So we have pipelines.
Fugitive emissions of methane.
Fugitive emissions of methane, which occur all the way, for the most part, back at the gas field rather than on the transmission system, which is pretty tight. The gas field, if you're sloppy at the gas field, oil and gas are often produced together. And in many places, there's nothing to do with the gas. They haven't built a pipeline to the oil field. This is true especially in new developments of oil like North Dakota with the shale oil. So the gas is then vented. Nobody's even trying to, it's not even a leak. It's just, it's an acceptance that we're going to be in a hurry and not bother to connect with a pipeline. That's going to change. It is changing. The major oil companies have already committed themselves to dropping their gas emissions related to gas production way down. Someplace like North Dakota, they realized there was royalties to be gotten if they could only sell that gas. You're venting a valuable product. And they started clamping down. So natural gas leakage is a serious issue, and it does reduce the competitiveness of gas relative to coal, but it really can be fixed.
Great. Jeffrey, Daniel, do you have any comments you want to add there?
I'm going to pass on this one. I'm not an expert on the natural gas or the collection and the natural gas grid side of things. So
we've done calculations where it is for greenhouse issues. It can dominate the entire calculation, a sloppy gas field.
I was just going to mention, as I put in my answer, that like the fugitive methane emissions are really not well understood. I mean, I think the fugitive emissions from coal and from coal like piles and the methane that just sort of naturally leaks from piles of coal sitting around power plants is something that hasn't been, even quantified until recently. And it's, these are questions that need to be grappled with. I think everyone would agree that natural gas is not the perfect energy source, and that in the long run, moving away from that is a preferable option if we can pull it off. And I mean, these are complicated questions for sure.
I agree with Jeffrey that the emission numbers have been terrible. They've been made up and then believed, which is a bad combination. Make them up, remember that you made them up. But there's some new, going to be private sector, non-industry satellite going up that will pick up hotspots of natural gas emissions. Indeed, to spot these places and then shame, if you like, any big emitter into cleaning up his act or her act. So you have quite a bit of change now in terms of the quantitative understanding of the methane emissions. They may be from natural sources too that we see. The oil and gas world is only responsible about 20% of the methane emissions. And even that number isn't that well known. A lot of things are going to get pinned down with the help of these satellites.
Yeah, two follow-ups. First, I'm told that if you hit show all in the QA area, you'll be able to see the answers. So hopefully that is that, and thank you to those of you who have mentioned that you can see them. We have a follow-up from one of our economists who will be speaking later today about that. And he basically says, should we bother with methane today when it is so short-lived? Why spend money on that today when it won't cause big harm in a century, yet carbon will?
That's a hard question. I mean, the natural gas is the cusp subject. The coal doesn't have the same number of arguments going forward. Gas is flexible, and it can, first of all, there are some costs, which are the distributed gas in the cities, like in the cities of the US, for example. They are hard, that's going to be hard to back out before you redo buildings. And so that's got to be taken seriously. Gradually, you can replace a gas furnace with electric heat pumps. There'll be a national program to do that, but it's going to be around a while. And then its complementary role to intermittent renewables is significant, I think, because they can ramp up and down, as I said, in its power output to compensate for a cloudy day. And in the multi-hour domain of storage, alternatives to storage, it's going to be competitive. We'll raise the cost of renewables if we don't use it. And we can use it coupled with carbon dioxide capture and storage. It could still be flexible. It'll be harder to do it once you add that to it, but it still has that role for a while. I think investing a whole lot further in the natural gas system may not make sense, but we can use what we have for quite a while in valuable ways.
We have a couple, I'm going to combine a couple of questions here, some of which I think were asked earlier in your remarks, Rob. What about the role of nuclear? in this decarbonization portfolio? And what about the role of small scale solar projects? For example, some that are happening in very small contact or small areas in this particular question highlights a project in Ohio. Nuclear, small scale solar?
Two quite different questions. Let me do the solar first. We did a study of New Jersey with solar and realized there was a whole category called mid-scale. There isn't any large opportunity to build anything like the size of the plants in the desert in New Jersey or Ohio. But there were 5 megawatt. Princeton University has a 5 megawatt, 25 acre establishment. So do several other college campuses. And that scale is important. And it tends to get forgotten about in between the house rooftop, which might be 5 kilowatts, and a desert, which might be 500 megawatts. There's a lot of room in the hundreds of, in the 1 megawatt type scale. It will play a role, maybe the dominant role in Ohio, as it is in New Jersey. Most of the solar in New Jersey is from that mid-scale. Nuclear look, we could talk for a long time about it. We have an industry that has disappeared from the U.S. Or is nearly disappeared. We are not able to build a competitive nuclear power plant at this time. Do we revive the nuclear industry, which will be very expensive? We watch other countries like China and Russia and South Korea take charge of the civilian nuclear power and then sell it all over the world because they figure out how to get the cost down. What would it take to catch up? And how do we have a nuclear system that doesn't lead to nuclear war? The particular nuclear type, there's many versions other than the one we've been building, called the light water reactor. There are many other versions. Is it time to start another one? China looked at all the alternatives and mostly is building the one that we built. There are many deep questions about the nuclear power system that we haven't gotten into. Waste management is another.
Great.
By the way, I'll be happy to carry on conversation with individuals who simply write me after this talk.
Yeah, there are a number of comments here in the Q&A as well. We previously touched on the importance of having community acceptance when attempting to shift our energy infrastructure to renewable sources. This seems like a task that is easy to say needs to be done, but difficult to execute in an increasingly politicized country. What steps do you think, or do you believe, need to be taken to ensure these communities believe these changes are in their best interest?
Let me pass this one to Jeff and Dan. Maybe Jeffrey.
I think that question was well put. It's really complicated and difficult. You know, I think we talk about the just transition and energy justice, and I'm going to be talking about this more in depth later today. I think at like 4 o'clock or 4 something. But you know, there's other types of justice like procedural justice and recognitional justice. And so procedural justice, is there justice in the decision-making process? Do people feel like the decision-making process to put a wind farm near their community, do they feel like they have the opportunity to contribute to that decision-making process? Do they feel like their voice was recognized and that they were heard and that their concerns were listened to and that they were, maybe not even addressed, but at least they were listened to and they felt like they were part of the process. Like I think that is a huge, and the research, social science research is clear as day, shows that, if people feel like that they've had a fair shake in the process, they'll be much more likely to accept the outcome, regardless of what the outcome is. And I think that's that's true for any kind of development, whether it's building a parking garage or whatever. And so I think that's one of the biggest points of that. And then another thing is just in terms of where we're putting these places, are we putting wind farms in sort of disadvantaged communities? Are we picking on places that sort of don't have the capacity to resist? Or I think, in terms of even more broadly speaking, I mean, we definitely need, if we're going to pull this off to get the types of renewable, generation that we need. Some sort of, I don't know about national, but some sort of coordinated sort of system or plan to cite these things and to make these decisions instead of like a very ad hoc nature that we have now.
One thing I want to pick up on, Jeff, is as you started this sentence, are we going to put the wind turbines in a disadvantaged community? I was thinking, and give the disadvantaged community the benefits, the rents, as they're called in economics, of having that turbine be theirs. I mean, if we think of all these as bads, then we think about it being wrong to send it to a developed, a poor community or a disadvantaged community. But if the income from that can be partially owned, it's like leases that are, and community solar, community wind, where there's co-ownership by a community that maybe is disadvantaged and has some benefit from it, then it's not clear at all that the goal is to keep it away from the poor neighborhoods.
I agree completely. I think the problem, I mean, the challenge is that I think, some people do see it as, I mean, in the current model anyway, people, especially people who aren't receiving the direct benefits, they do see it as a cost and not a benefit. But I think the community-owned model that you're discussing, shows huge promise. And in the United States, I think there's 2 or 3 wind farms that are truly community-owned out of the, tens of thousands of wind farms that are there. And so, again, that sort of points to this sort of need for a larger sort of rethinking of how we site these things and how we organize, ownership and the siting.
I encourage the audience.
On that note,
yeah, go ahead, Jeff.
Well, I was just going to say we are 2-3 minutes into our break. I'm happy to have you guys continue to chat about this. We are foreshadowing quite well a number of the issues that will come up in following sessions, especially in the next, well, in following sessions. So I want to be sure. I mean, again, feel free to continue to chat. We will move to what does it mean to go renewable at 2:30. But I want to be sure that we all have the opportunity to thank Professor Socolow for joining us. And while I will borrow a phrase from my PhD advisor, who I know Professor Socolow knows quite well, we have exhausted the time, but not the topic, but we have not yet exhausted the time or the topics because we still have 7 more hours of this symposium over the next 2 days. So again, I want to be sure to thank you, Rob, for joining us. And if you want to continue chatting, I will work on trying to address some of the questions in the Q&A. And at 2:30, we'll move on to the next session.
Well, thank you very much. It was an honor to be part of this. I wish you all the best in the next 7 hours.
Thank you, Rob. And so we'll reconvene at 2:30 Eastern time in 5 minutes for the next session, which will feature somebody you've now seen already. Professor Daniel Gingrich will be speaking to us a bit. And then later in the day, you'll see Professor Jacquet show up again and talking in more depth about some of these social and community issues. Until then, see you at 2:30.
I'm not sure who's live here. Any of you? Me? I think we are gone.
Welcome back, everybody. Going on that very illuminating talk from Professor Socolow, we have a session now evolving the electricity system towards renewable energy. In this session, we will hear from Professor Daniel Gingrich, who has a joint appointment in the Departments of Civil, Environmental, and Geodetic Engineering and the Integrated Systems Engineering departments. I failed to mention before that he's also a core faculty of the OSU Sustainability Institute. We're going to have Professor Cinnamon Carlaran from our Moritz Law School here talk about regulatory and governance issues associated with renewable electricity. And we're also going to have Professor Shashansi, who's in the Integrated Systems Engineering department, talk about how the electricity system works. So we'll go Daniel, Ramteen, and then Cinnamon, and then again, 10 minutes each, and we'll follow up with a 15-minute panel discussion. Daniel, take it away.
Okay, let me go ahead and share my presentation. Okay, so as Professor Bielicki mentioned, I am going to talk about electricity technologies and how we generate electricity today and the technologies we could use to do so in the future. And as a general rule, the way that we generate electricity for almost all of the systems I'm going to talk about today, with one exception, is by using some fluid to move a turbine around. And by moving a turbine around in a generator, we can convert mechanical energy into electrical energy. And I want to start off by talking about what are known as the WWS sources: wind, water, and solar, which are the ones that people talk a lot about when we talk about what we want more of in our future electricity grid. Starting off with water, and in particular, thinking about falling water or hydropower. This is a picture of Grand Coulee Dam. It is the biggest hydropower plant in the United States, located in the Pacific Northwest of the US. And the way that hydropower systems work is that you have that dam that builds up a reservoir of water, and as water moves from the top of the reservoir down to the water below, that motion is what's spinning that turbine that I talked about and generating the electricity. We see a similar force that works for wind power and wind turbines, like this one at the Bowling Green Wind Farm in outside of Bowling Green here in Ohio, in which the motion of wind is what's spinning the turbine blades, and the motion of those turbine blades is what's being converted into electrical energy with the generator. The one technology I'm talking about today that does not involve the motion of a turbine is solar PV. This is also my favorite picture of solar PV panels that I found because it has Cosmo the cat, and I have no idea about the history of Cosmo the cat. I just know it appears on official social media for the Department of Energy. And so I want to know more about that. But the way the solar panels behind Cosmo the cat work is that they are absorbing sunlight. And the sunlight, when it's being absorbed by the materials within the solar panel, it's exciting the atoms within the panel. And the excitation of the atoms, the energy they're absorbing, is being used to eject electrons, to release electrons into the rest of the panel. And by releasing the electrons into releasing the electrons from the atoms, you can create a charge gradient where you have positively charged areas where the electrons were, and a negatively charged area where the electrons end up being, and you can harness that charge differential to create an electric current. And so these are the three big technologies that a lot of people are talking about when it comes to renewable energy resources. But there are some challenges when it comes to using these energy resources. And one of the big ones is just where we actually have these resources available. And this is a map showing you where hydropower dams are in the United States. That's what those circles represent, is the hydropower plants in the US. But if you look behind those locations, you also see this green shading. And that green shading is a way of thinking about the potential to build hydropower throughout the United States. And you see that there's a lot of rainfall, a lot of precipitation and runoff that we could use to power hydropower dams on the eastern side of the US and along the Pacific coast of the US, starting in about the San Francisco Bay Area and going up to the Canadian border. But you'll also notice these big parts in the middle of the country and in the southwest of the country where there's not a lot of precipitation and not a lot of elevation differences in some of them, especially as someone from South Dakota, let me tell you, it's a very flat state for part of it. And so you're not going to have a lot of hydropower resources there. But that's where these other resources that I've talked about can come into play. So for instance, we can think about the use of solar and how there's a good potential to build solar PV and solar thermal plants in the American Southwest that we can use to generate electricity there. And then there's also this wind in the middle of the country where there's a lot of abundant wind resources, as we saw in the map that Professor Socolow showed us earlier. But this is just one of the challenges that we run into with some of these resources, especially wind and solar. Because something else that Professor Socolow mentioned was that these are intermittent resources. They're not always available. And that's going to cause a challenge for the way we operate our grid. And to drive this point home, I want to show what's known as the duck curve. Because if you look at the blue lines and the orange lines, it forms something that looks kind of like a duck with a tail, its little body, and then a beak. But this is the duck curve representing the electricity generation and demand for California on October 22nd, 2016, with the blue line representing California's total demand, the orange line representing how much electricity was demanded from the grid, and the gray line representing the amount of electricity that was generated from solar. And what we can see looking at this grid, or looking at this figure, is that there's periods where you just don't have the sun shining. And solar generation is variable. And we see similar trends for wind, although it tends to be a bit different. You don't have wind as much during the day. It's more of a nighttime resource, but you still have significant variability in the amount of wind electricity that can be produced from a wind turbine. The other thing that's really important to know in this grid, or in a figure like this, is that we're going to need other types of generation. Because when the sun stops shining in California, and we also see it in places like Hawaii that also have abundant solar generation, you have this massive uptick when people come home and turn on their TVs and start to cook dinner and turn on all their lights. And so we're going to need electricity that we can dispatch, that we can control when it turns on. And that's a lot of the other sources I'm going to talk about today are what are known as more dispatchable energy. Alternatively, as Professor Shio-Sansui will mention later on in the next talk, we could also store energy. So we can store that solar that we're producing for later use, or we could shift our demand to be more evenly or to better match renewable energy resources. But I'm going to talk about other sources of energy that we can use because there are other sources of energies that we do use for our electricity grid, starting with nuclear power. And this is the Perry nuclear plant up in northeastern Ohio along Lake Erie. And the way that nuclear generation works is that we have these nuclear reactions. As the nuclear reactions proceed, you have heat that's released, and that heat can be used to either boil water or just heat up water pretty hot, but keep it under pressure so that it doesn't boil, it stays a liquid water. And either that steam or that hot liquid water is what's spinning the turbines and generating electricity. Another low carbon source of dispatchable energy that we're starting to see more and more of is geothermal. And this is the Steamboat Springs geothermal plant out in Nevada. And the way that geothermal energy works is by leveraging the heat in the earth beneath us, hundreds or thousands of meters below us. What we can do is we can extract hot water and bring that hot water from hundreds or thousands of meters below us up to the surface. We could then either flash that hot water to produce steam, or we can just use the hot water directly itself. And that can then be used to spin the turbine blade, generate electricity, with the steam or hot water returned back underground to be reheated and repeat this process. So those are the low carbon sources of dispatchable energy. There are also more carbon intense sources such as biomass. This is the Desert View biomass plant. It is located in Riverside County, California. And at this particular facility, what they do is they take wood and combust that for thermal energy that's then used to spin the turbine blades. But you don't necessarily need to use woody biomass. There are other biomass sources that can be leveraged in order to produce and generate that heat. Up next, we have natural gas, and this is the Hanging Rock Energy Facility in Southern Ohio. It's one of the largest natural gas plants in the state. And here we have natural gas that's being combusted. And then the heat from the natural gas there's typically a first pass in which just the hot combustion gas is used to spin turbine blades. But then that hot gas can then be used to produce steam, and that steam can then also spin turbines in order to produce electricity. And so natural gas plants tend to be more efficient than coal plants, like what this one, the Gavin plant, which you just have the steam part of that cycle being used to generate electricity. Here at a coal plant, as the name implies, we are burning coal to generate the heat that's used to make steam. And those last three processes I talked about, the biomass one, the natural gas one, and the coal one, are all focused on ways, or are all combustion processes. And so to a certain extent, they are going to release carbon dioxide as a result of combustion. But also, as Professor Socolow mentioned, we can capture that carbon and use it and sequester it or store it underground. And in doing so, we can actually reduce the amount of carbon dioxide that's emitted as a result of these processes. And for biomass, what we can do, and we'll talk about in a later session, is that if you are growing biomass specifically for this purpose and then you catch it, it takes carbon dioxide to grow biomass. And so you can remove carbon dioxide from the atmosphere before combusting it and then storing it underground in order to reduce atmospheric CO2 levels. And I want to wrap up, because I know I'm quickly nearing the end of my time, by just saying that CO2 is not the only factor that matters, or greenhouse gases aren't the only factor that matters when it comes to thinking about what we want our future energy grid to look like. For instance, on average, it takes about 190,000 square meters of land in order to build a hydropower dam for every megawatt that we're going to produce, that dam will have capacity for. On that same 190,000 square meters, you could build a nuclear plant that could produce about 186 megawatts. And so there's substantial land trade-offs for some of these energy resources. If you think about the water it takes to make a solar panel, it's about 73,000 liters. But the same 73,000 liters of water it takes to make a solar panel could be used to build about 4.4 megawatts of a natural gas plant. Now, the operating of that natural gas plant is going to use a lot more water than solar panels. But if we think about just the manufacturing stage, that's a trade-off that we're going to have to grapple with. And then finally, on average, an onshore wind farm will produce about 0.36 full-time equivalent jobs for every megawatt of capacity that's built and operated. But if I was to invest instead in natural gas, I could produce about 33% more jobs. On average, a natural gas plant will produce about 0.48 jobs per megawatt. And so there are complicated trade-offs that we're going to have to grapple with as we think about what we want our energy system to look like in the future. And it's not going to be simple, and it's going to be complex. And we're going to have to learn to live with that over the next couple decades as we move our grid in different ways to understand what these trade-offs are looking like and be cognizant that we're making them. So with that, I will look forward to questions in the Q&A period at the end.
Great, thank you, Daniel. Ramteen.
All right. Thank you. Let me just hop a little something on the screen here. All right, so hopefully folks can see that. So thank you to you, Jeff, for inviting me to speak here today. And Daniel and Jeff did a good job of queuing up what I'm going to be talking about. So actually, a lot of what I'm going to start off talking about will be repeated a bit from what Daniel said. I'm going to talk a little bit about the basics of how electricity systems work, and then the potential need for energy storage if we are going down a pathway of using high penetrations of renewable energy to achieve decarbonization or other types of environmental or energy policy goals. So to start off with, when we describe a power system or an electricity system, what does it consist of? And I think this figure kind of illustrates at a high level what the electricity supply chain consists of. There are really three major steps to get electricity to the end customer. You generate it. Now, traditionally, and this was really because of scale economies, traditionally our power systems were built around having massive centralized generation facilities. Then you would transmit it and transmitting it would be over long distances. And for reasons of the basic physics of electricity, you transmit at high voltages because that reduces the amount of energy that gets lost in that transmission process. The final step then is you distribute it. Distribution is done at lower voltages, and that's basically because lower voltages are less likely to kill people. And that's basically, you know, for the first century or so of development of electricity systems in the modern world, that's kind of how we have done things. Now, what is sort of the key challenge of keeping the lights on in the power system? And Daniel hit on this and alluded to it in what he said. And I am oversimplifying quite a bit, but really I'd say the key grand challenge of keeping the electricity system working is that you have to keep supply and demand in constant balance. If supply and demand are not in balance, then you basically create problems, let's just put it that way. In the old days, how did we maintain balance between supply and demand? Well, it was done using a combination of inertia in those rotating generators that Daniel mentioned, and then using control as well. So what do I mean by inertia? Well, basically you have rotating parts in all these steam turbines or other generating facilities, and the rate at which those are rotating, well, they can slow down or pick up a little bit of speed if you have slight imbalances between supply and demand. And that inertia, basically, that can kind of cover imbalance between supply and demand on a sub-second basis, or maybe for 1 or 2 seconds. Beyond that, you have to move to the concept of control. The concept of control is basically, well, you have to actively adjust the output of generators. And so what Daniel was saying about fossil fueled or nuclear generators, one of the things that traditionally we like about those is that you actually can control their output. So it makes this challenge of maintaining supply and demand a little bit easier. As I note here, to some extent, transmission can help you because when you have a transmission system, you're balancing supply and demand over a larger area. So supply and demand deviations, they can sort of cancel each other out if you're doing this balancing process over a larger footprint. The other nice thing that transmission helps you with is it helps manage the challenges of maintaining supply and demand balance if you have, let's say, a generator failure. Because if a generator fails in a small system, that can represent a large proportion of the supply. If you're operating over a larger footprint, one generator failing is not as catastrophic for maintaining that supply-demand balance. All right, so what are the challenges that renewables are raising for us now? I have a few figures here that illustrate, and again, not all of them, but it gives you a sense of some of the issues that we have to deal with. So one, first and foremost, is that most renewable technologies, geothermal, biomass would be notable exceptions. They're less controllable. So a wind generator, a solar generator, well, we have some flexibility to reduce their output, but their output has an upper bound based on ambient weather conditions. So yes, we can feather the blades on a wind turbine if we want to reduce the output, but whatever ambient wind speed is, that gives you an upper bound on how much you can get from a wind generator in real time. Another challenge is that most of these renewable generators, wind generators included, they don't actually provide this inertia that we've used traditionally for maintaining supply and demand balance. Wind generators, most of them use what we would call asynchronous. Most of them are asynchronous resources, so they don't, technically speaking, provide this inertia that we've relied on historically. That's just kind of an artifact of how we integrate wind turbines into electricity systems. renewables might not be available when or where they're needed. And that's illustrated in two of these figures here. So on the left-hand side here, this is the duck curve that Daniel mentioned. So you can get into situations in which, and this is starting to happen in California today, basically the belly of the duck gets so far down that adding more solar resource doesn't really do a lot in terms of meeting electricity supply needs, because it's really the top of the head or the top of the tail here. That's where we have supply issues. Another example here, this is taken from the state of Texas. The way that Texas is kind of laid out geographically, so they're very good wind resources in West Texas, but all the population centers are in East Texas. And so the only hope of tapping those resources traditionally has been using more transmission facilities to be able to move that wind resource from the west to the east. Now, what is the potential role of energy storage in helping to address some of these issues? And what I have here, what this figure and the figure on the next slide are showing, is it's giving, and the numbers on the left-hand axis don't really matter because this is just an illustrative case study. But what it's showing is basically what a capacity mix might look like if you're trying to achieve different levels of carbon reduction compared to a business as usual case. And what we were looking at here is we were looking basically at technologies that are available today. So we weren't really looking at technologies that might be 10 or 15 years into the future. And what we see is that the energy storage actually has a relatively, at least for moderate levels of carbon reduction, has some, but a relatively limited role. So we do build a little bit of compressed air energy storage. And you see some Ks being built up to about a 95% carbon reduction requirement. But most of the balancing between supply and demand, the way that we're actually achieving that is by using natural gas-fired generation. So basically, you can get about 85 to 90% reduction in carbon emissions just by building lots and lots of wind and solar. And then on those days that are cloudy and you don't have wind resource available, you basically use natural gas-fired generators to provide that balance between supply and demand. Now, once your carbon reduction target gets very stringent, you can't rely really on natural gas anymore. And now you have to start building massive amounts of wind and solar, and then you have to start building massive amounts of energy storage. What does this look like in terms of what it would cost? And again, the numbers themselves are not all that important. Really, the relative scales are what I'm trying to convey here. With technologies that are available today, we can get about 85% carbon reductions compared to business as usual, relatively inexpensively. Basically, when I say relatively inexpensively, what I'm saying is that the incremental cost of energy is smaller than what people estimate to be the social cost of carbon. The last 15%, though, is quite expensive. So why is it quite expensive? Well, what I'm showing here, this is an illustration of, so we were looking at actually a different solar technology from the one that Daniel talked about, which is what's called concentrating solar or solar thermal. And unlike a photovoltaic panel, which basically uses the photovoltaic effect, which is excitation of electrons in a semiconductor, what a CSP plant does is it basically it converts sunlight into thermal energy and then basically just uses that thermal energy to run a steam turbine the same way that you would a coal or a gas-fired plant. The nice thing about CSP plants is it's very, very cheap to put thermal energy storage into these things. Basically, you just build these massive vats with a molten salt in them, and you can use those to store electricity for hours on end. Now, despite the fact that you can put thermal energy storage into these CSP plants relatively inexpensively, what the figure here is showing is if you wanted to rely on CSP with thermal energy storage, basically to provide this reliable supply to maintain supply-demand balance, you still run into a handful of days in winter when there's just prolonged periods of cloud cover and you just cannot get that level of electricity supply from your CSP plant. So what this figure is really illustrating is that really the grand challenge and the energy storage grand challenge for achieving kind of that last 15% of carbon reduction, and that's what the last bullet here says, is a scalable and economically viable technology that could be used for seasonal energy storage. Basically, we don't have a technology that makes economic sense to cycle once or twice a year. And what I mean by cycle once or twice a year is you basically charge energy into the storage medium in the summer, and then you discharge that energy in the winter when you may have 3 or 4 or 5 days consecutive with very poor wind and solar resource. So that's really from my perspective, the grand challenge that energy storage still has to kind of fulfill or achieve if we want to be able to get that last 15% of carbon out of the electricity mix in an economically viable way. With that, I will hand it over to the next speaker and looking forward to discussing during the Q&A.
Great, thanks, Ramteen. Cinnamon, you're up.
All right, hi everybody. I recognize that we're running a little late, and so I'll try to be brief in my remarks. But first I want to say a huge thank you to Jeff for having me here and allowing me to speak, but also to the Sustainability Institute for beginning to really bring together these conversations and to help us address these important questions. And I also want to say a thanks to Jeff and the Institute for ensuring that this conference really has a diverse set of voices speaking, diverse in a variety of ways, disciplined perspectives. That's often hard in the energy context, but I think it's incredibly important. And so thank you for that. And with that being said, I'm going to talk about something almost completely different than what you've heard before, drawing from the first two talks, but really focusing on the law and policy side of energy, and in particular kind of governance questions. And again, we are a little late, and so I'm going to give you a quick roadmap of what I want to do. I'm going to walk through it, and then I'm going to try to leave some time for questions at the end. So first, what I want to do is I want to very briefly discuss the whole concept of a U.S. energy policy. And then I want to very briefly discuss the role of the federal government in energy policy, and then the relationship between the federal government and the state governments, but then using a few states and kind of the actions that those states are taking to really emphasize that no matter how much development we have with wind technology or solar or geothermal, if we don't have the right governance system in place, like either the incentives or the removal of disincentives, not much can happen, or we can have a lot of inconsistency. And so I want to kind of really elevate the law and policy and governance discussion so that it's part of thinking about how we move towards a sustainable energy future. And I do want to just kind of highlight that while I'm not going to have the chance to talk about it today, the questions of equity and justice have to be front and center in everything we do. And just kind of note that the Department of Energy has recently recognized these questions and brought them to the forefront by creating a new Deputy Director of Energy Justice. And so questions of energy justice are starting to kind of infiltrate federal energy law and policy. Okay, so first, what is U.S. energy policy? Do we have a U.S. energy policy? Many people would argue we don't have a U.S. energy policy, that it's very haphazard over the years. There's been a lot of variations. But I would like to suggest that we have historically had a US energy policy, and that US energy policy really needs to change in order to move towards a sustainable energy policy. So kind of historically, US energy policy has really tried to ensure a few things. The first is ample and reliable sources of energy, so reliability. The second is low cost energy, so really affordability. The third is that it's really propped up historically very traditional energy sources, fossil fuel and nuclear. And it's done so with kind of heavy infrastructure, really incentivizing the growth of kind of these large investor-owned utilities, and that it's done so in a very complicated and often messy way within our dualist kind of federal system. One of my colleagues in energy law described the energy policy in the US thusly: the United States government has served as partner to constructing a fossil fuel policy intent on bringing to market cheap and dirty energy. Didn't necessarily mean for it to be dirty, but it turns out it was. But that is kind of the roots of US energy policy. And so what we're doing today, what we're thinking about, what you guys are all thinking about on the energy and science side, and what we have to think about on the law and policy side, is how to keep that reliability and affordability while then adding this kind of third pillar of sustainability. Now, okay, that's the kind of energy policy piece. Now let's talk about the federal government for just like half a second, and then we'll talk a little bit about states. So first and foremost, it's important to understand that the federal government and federal law and policy plays a really, really important role kind of in the backdrop of everything that happens in the context of energy policy. And we don't have just the time to discuss kind of either the history or the architecture of federal energy law, but kind of suffice to say for our purposes here, it's very layered and complex. And there is a lot of capacity to use law and policies, either a very powerful enabling tool or as a really dramatically limiting tool as we try to move towards a kind of just transition towards clean energy. Just a couple of ways in which that can happen. So historically, everything that happened in kind of federal energy law really led to the construction of what we think of these kind of vertically integrated utilities and kind of monopoly-based system that kept out competition for many, many years. It was only kind of in the 60s and late 70s that the federal government passed legislation that allowed some competition by allowing some of our small generators to kind of access the transmission lines. This is what kind of the first foothold renewable energy actually had, and even being able to compete in this system. Now, I'm not going to spend time on the system because I know Ramtin actually talked a little bit about generation, transmission, and distribution. But I want to just kind of highlight three ways very briefly that the federal government can either enable or kind of limit the growth of renewable energy in the future. The first is the federal government through both law and policy, and they are distinct, of course, has the capacity to really address what I think is one of the biggest impediments to the growth of renewable energy across the United States, which is problems with our transmission system. And so with respect to transmission, it needs a lot of smoothing out. So we need an expansion to accommodate renewable energy, and we need smoothing out to address bottlenecks. And we also need market regulation to ensure competition and to ensure that small generators can access the system. And so FERC, the Federal Energy Regulatory Commission, and the Department of Energy have a really, really significant role to play in this context. They can play important roles in both figuring out where the new transmission lines needed. So kind of they've done a variety of studies, some of that background R&D. They're also helping kind of untangle these complex questions of who should bear the construction costs of those new transmission lines. Historically, they've been privately funded, but there's questions about that. So kind of figuring out where those transmission lines should be, who should pay for them. And then also, of course, protecting the grid from increasing number of physical and cyber attacks is really, really important. And the federal government, also FERC in particular, has an important role to play there. And all of these things will be absolutely necessary for transitioning to a clean energy future. They're kind of fundamentally important to doing any of the things that we've talked about today, is having that healthy functioning grid. And so the federal government plays an important role there. Two other areas where I want to very briefly mention is, what the federal government does with both kind of environmental law and energy law is really important in the context of, either subsidizing existing sources of energy. So, there's a lot of subsidies for fossil fuels and nuclear energy that still exists at the federal level, or incentivizing, renewable energy, renewable technologies. So the federal tax incentives for wind have been incredibly important, and you can kind of chart the growth of wind through whether or not certain tax incentives are available or not. And so, subsidies, incentive-based structures, all of these things are important. And so having a federal that is supportive of and enabling a healthy electricity system, and is also kind of providing the right sorts of incentives or minimizing the disincentives for the growth in renewable energies will be fundamentally important. Now, with that being said, energy law is also really, really about the states and what the states are doing. So every state has its own electricity system. Some of those systems remain kind of what we would think of as largely traditional or conventional, controlled by public utilities with very little competition, still very vertically integrated. Others have begun to travel down a path of deregulation that tries to encourage and incentivize more competition. Different states have also taken very, very different approaches to trying to diversify their energy sources through, for example, the adoption of renewable portfolio standards or other policies and kind of incentivizing growth in renewable and alternative energy sources, including, for example, incentives for growth in very particular sources of energy, such as solar carve-outs, where they require that the utilities source a certain amount of their, or produce a certain amount of their electricity from solar energy. States have also taken decisions that really very clearly and dramatically hamper the growth of renewable energy, including, for example, Ohio's HB 6. That's not the only one, but it's one that many of us will be familiar with. Now, so the part of the point here is that no matter what technologies exist, state law and policy is really important to thinking about what's going to actually happen. And so I want to talk very briefly about two renewable giants, kind of in renewable giants, but also political and economic giants in the United States, Texas and California. And then if we have a moment, which I don't think we will, I could also talk to you about the Midwest, where Ohio and Indiana, I will tell you, are lagging, whereas Iowa and some other states are kind of much more, made much more progress. But let me just mention Texas and California, because they're the giants in developing wind power and solar power, but they've done so in very different ways to provide models for thinking about the way in which law and policy can incentivize growth in renewable energy technologies. So there's, in excess of something like 27 gigawatts of wind in Texas and 25 gigawatts of solar in California. California was an early and aggressive mover on solar. Texas was an early and aggressive mover on wind, but in very, very different ways. And also, I just want to highlight that Texas is actually about to catch up to California in solar and perhaps even surpass it. And I should say I am a Texan, but I'm equally critical of Texas as I love Texas. But okay, so how do they do that? And what does that teach us? So in California, the way in which solar grew so quickly there was due to regulation, a really kind of law and policy-based decisions. In 2006, for example, and I'm just going to sketch it out for you very briefly, but in 2006, the California legislature enacted Assembly Bill 2021, which required its traditional investor-owned electric and gas utilities to reduce their electricity consumption by 10% within 10 years. And then subsequently in 2015, California enacted Senate Bill 315, which was the Clean Energy and Pollution Reduction Act, which required certain additional changes with respect to clean energy. And then finally in 2018, California adopted a legislation that was unique to any law in the United States, which ensured that 100% of every new construction that was built that was under 3 stories high would have to have solar panels on it. So in other words, they were taking a variety of steps to require their investor-owned utilities to invest in renewable energy, to source their electricity from renewable energy, and ultimately requiring construction to have renewable energy technologies. And as a result, you see this massive growth in solar, and it has not been uncomplicated. I just don't have time to discuss the complexity. On the other hand, Texas did almost the exact opposite. Texans historically, we don't like a lot of regulation, right? Like, we're a free market economy. And Texas actually took advantage of that kind of free market approach to grow its wind energy capacity. So we're the kind of wind power leader. We're looking to rival California's solar dominance, but we're doing so in an opposite way than California moved towards solar technologies. So Texas operates based on these kind of free market principles, and we have our own kind of ERCOT, the Electric Reliability Council of Texas, which is like, I think Ramtin talked about it, which is the nonprofit entity that manages the Texas electricity market, manages supply and demand, and it uses price signals, okay, unlike some others. And so it uses price signals to allow free market forces to solve kind of some of the technical issues to meet supply and demand. And what Texas has been able to do has been very successful in meeting the electricity needs of the state at a very low cost and providing a huge amount of power, including more and more power from renewable sources. Now, part of the reason Texas has been able to do this is because land and labor are cheap, for better or worse. There's problems there. And also they make it really much easier to get permits than in other contexts. So reduced regulation in Texas has meant that it's easier to build projects and get permission to sell power on the grid. So it's kind of easier to innovate. And I'm going to kind of stop there probably because I know that we're almost out of time. But part of what I want you to have as a takeaway is that governance structures matter, law and policy matters, what the federal government does, how this, the states have historically served, in the traditional capacity as these kind of these laboratories of innovation. And they've certainly done that in the energy context with huge variation across the states, not just because of whatever renewable energies are actually kind of available there, but also because of the politics of the state. So we have a lot to learn from looking at the states about how to kind of incentivize and also how to inhibit the growth of renewable energy. But ultimately what we're really going to need is, strong federal leadership and federal signaling to meet with those states to kind of ensure this kind of really deep, long-term, sustainable move towards clean energy. Thanks.
Great, thank you, Cinnamon. Thank you, Danielle, and thank you, Ramtin. We have some time for the panel. We have a scheduled break at 3:15, but we could, well, in 3 minutes, but we can eat into the break as long as reconvene at 3:25 for the negative session. There's a fair amount of activity in the Q&A. One of the things I want to bring up that we haven't talked much about yet is hydrogen. And what do you see from law, policy, technical, and system integration considerations for hydrogen?
I think the big challenge that I see for hydrogen is thinking about how we build a hydrogen distribution network across the country. Will we need to build a separate grid for hydrogen, or are there ways that we can use like our existing natural gas infrastructure to distribute both natural gas and hydrogen, or just hydrogen in the future? And if we do use the natural gas grid for some point when we have both natural gas and hydrogen in the grid, how are we going to maintain and operate that so that it can handle those dual infrastructures, given that there are trade-offs in terms of the performance of natural gas systems that have hydrogen contamination in them? There's safety issues you start to run into. And so I think thinking about the distribution aspect is going to be an interesting technical challenge for hydrogen going forward.
The only thing I would add, just from an energy storage perspective, I think the technology still has a way to go in terms of cost and performance characteristics. I think that's the only thing I would add on top of the infrastructure, transportation, and distribution challenges, questions.
Cinnamon, there's been a renewed interest in hydrogen as of late. Is on the law policy side, are you aware of that being grappled with, some of the complexities around hydrogen?
So I don't know. I mean, I haven't worked or thought at all about hydrogen, so I can't answer that question. I was trying to answer the question, one of the questions in the chat box about equity, but I don't know a lot on the law and policy side about hydrogen or what's going to happen in that space.
Okay, great. One of the things that Cinnamon you highlighted pretty well was the difference in approaches between California and Texas, which very much have approached, Texas has a long history of being fossil oriented and has approached renewable space very much from the wind side. California has a very long history of having some of the more stringent and strict environmental regulations. How about, what are some of the considerations when a state goes in a particular direction, and how might that affect what happens in other states? And this is actually a question for all of you.
I was unmuted. Okay, I think that that's a great question, and I think there's a variety of things to think about. The first is, when a state takes a particular direction, whether it's California or Texas or somewhere, and they're kind of creating a strategy that allows the growth in a particular source of renewable energy, whether it's wind or solar, that experimentation is important because you can learn a lot from it. You can learn a lot about what works and what doesn't work in terms of laws and policies incentivizing it. As the question pointed out, you can also see kind of what the regressive impacts might be of trying to diversify the grid. It also can have really interesting and important constitutional implications. So for example, California tried to adopt some policies where they weren't going to allow for any out-of-state energy that was dirty to kind of come across state lines, which then raises really interesting kind of dormant commerce clause questions, some of which are still kind of sitting out there. So there are some really kind of important legal questions sitting in the background. But I would say that I think the most important thing to think about at this point is kind of what experimentation can teach us about what works, and also as we start to see the growth in renewable energy kind of writ large, what it tells us about the capacity of our electricity system to accommodate that, and to learn from it.
So, and I think in addition to the learning about policy, another important thing that happens that Cinnamon brought up briefly, but I want to make a bit more explicit, is that we have learning by doing when it comes to how these technologies are actually built and operated. And that also serves to reduce the cost. And so policies that states put in place to incentivize or encourage development is also going to reduce the cost in other places where we might build those technologies. And that'll be helpful in making them more competitive across state lines in places that may not have policies in place that will would subsidize or encourage those technologies to the same extent.
Yeah, I think to add to that, we've seen that to some extent with California. A number of years ago enacted an energy storage mandate on its three large investor-owned utilities, and I think to a large extent those utilities have gained familiarity with using these technologies, and it's also kind of provided a almost like it's created, in some sense you can think of it as artificial demand. Well, artificial or demand by fiat. So it kind of gave the industry the opportunity to develop the supply side to meet that mandatory demand. And part of the vision was, you allow the industry to get a foothold, you allow the electricity industry to gain familiarity with these technologies, and then that allows these things to scale up. I think one of the issues, at least from the decarbonization perspective, is in this country and many other countries, we're not willing to take the efficient policy measures, so pricing carbon or something like that. So we use a lot of these very, to be blunt, core policy instruments like renewable portfolio standards or subsidies for renewables, which they move you in the direction, but they do it at very high cost compared to more efficient policy measures.
Great, yeah, thank you. I think what we've highlighted in this session is that there's a lot of complexity from the technology, the resource, the system, and the law, policy, and behavior side. And as with the end of our discussion with Professor Socolow, we have exhausted the time, but not the topics. We still have a few more hours to go, and we'll cover a lot more topics, and we'll reconvene in 5 minutes. at 3:25 Eastern time for the next session on what does it mean to go negative. Thank you, Cinnamon. Thank you, Ramteen, and thank you, Daniel. I really appreciate you conveying your knowledge and wisdom. Thank you. Welcome back, everybody. For those of you that are just now joining us, I'm Jeff Bielicki. I am an associate professor here at Ohio State with a joint appointment between the College of Engineering and the Glenn College of Public Affairs. And this session is going to be negative about how we various ecological and technological approaches for how we can extract carbon dioxide from the atmosphere while still producing things that are useful. We're going to have three of our colleagues here at Ohio State talk. Professor Brent Songen on the ecological approaches and Professor David Cole on the more technological approaches. And we'll round it out with some consideration about how behavior and incentives can help to manage us keeping the carbon out of the atmosphere. And that will be by our colleague, the social scientist, Robin Wilson, in our School of Environment and Natural Resources. So Brent, take it away.
I guess we got to unmute. Thanks a lot. Thanks for inviting me, Jeff, and the rest of the committee put this together. I really appreciate being here. I guess this is the session where negative is good, so that's I guess a good thing. I want to start out by sort of talking through what is net zero with maybe a simple graph, probably some information that many of you already know. So I apologize if this is a little bit slow. I'm going to speak really fast, but I apologize if you already know all this, at least the first part here. Hopefully some that you don't know. But of course, what net zero kind of means is that, we're running around with our, flying around, at least, well, we haven't really been doing a lot of that in the last year or two, but driving around, some of us still do. And we're using a lot of electricity. So we're putting carbon molecules up in the atmosphere. And we can, of course, use then photosynthesis to take some of that out of the atmosphere. So we can sort of grow trees or grow crops and put some of the carbon in soils or keep it in ecosystems. And if we really want to, we can take some of that carbon from the trees and carbon from the crops and take it and burn it for electricity, and then take that carbon and stuff it down in the ground and carbon capture and storage. So this BECS option, biomass, energy and carbon capture and storage, is a way to take carbon out of the atmosphere and put it back down where it sort of came from in the first place, or at least some of it came from. So these are kind of ways to sort of net out what we're putting in the atmosphere. What net zero basically means is that we want to try to have this stuff zeroing out some of the stuff we put in the atmosphere. And if you're an entity and you can actually get to net zero, that's kind of a great thing. So who can actually do that? Well, it turns out anybody can actually do that, right? So countries can do it. In fact, that's what the Paris Agreement tries to do, is that by 2050, everybody's kind of net zero around the world, and then the whole world's net zero. So we've got somehow to a point where we're taking as much out of the atmosphere as we're putting up there, which means we've got to reduce what we're putting up there and increase what we're putting, into either biological storage systems or underground. Sectors can do it, as we'll talk about in a second. The forestry sector actually is net zero and has been for over a century. Businesses can do it, universities can do it, households can do it, and individuals can do it. From a policy perspective, probably, it makes the most sense for countries to do it and then develop policies that would not make individuals as an individual be, carbon neutral or net zero, but instead be efficient about it and try to make sure that the costs are as cheap as possible across all actors in an economy. So how do you do it? You basically reduce your emissions as much as possible. And then the rest of it that you can't reduce, most people think that's kind of transportation for now, and at least airline transportation, a decade or two from now after we go to all electric cars. And then the rest of it that we can't get sort of out of the rest of the economy, the rest of the emissions we can't get out of the rest of the economy, we do it with carbon dioxide removal. That is, we take it out of the atmosphere through growing things using photosynthesis. So we plant some trees, we delay some timber rotation, we let trees grow in places we might have got rid of them, or we convert some land that's not in conservation tillage to conservation tillage and stuff the carbon down in the soils, or we grow biomass, burn it for energy, and stick it underground, right? And at the end of the day, we hope that some of our emissions and our carbon dioxide removals should be zero. So what are some ecosystem storage locations around the world? It turns out that there are just an enormous number of them, and that actually we could do a lot of this stuff. Forests and other ecosystems over here could potentially sequester around 14 gigatons or 14 billion tons of carbon dioxide per year. That's kind of technical potential. Most of that's in afforestation or reforestation. There have been some great studies in the last couple of years that have shown that this potential is really, really huge. Sustainable forest management is another one, not nearly as big as afforestation or reforestation, but it's not so bad. In the agricultural side, we can do things. Agroforestry in the rest of the world turns out to be a really big one. It's probably 7 gigatons of the total 9 gigaton technical potential. Soil organic carbon is also a reasonably large one. Biochar, not quite as large, but these are ways to take carbon out of the atmosphere and put it down. into the soil. Biomass energy, carbon capture and storage, estimated to be about worth 2.5 gigatons of carbon dioxide per year. And then there's these other ones in the land-based system, reducing emissions from deforestation, things like that, which aren't really drawing it out of the air, although they may be in a way, but they are also actually avoiding an emission. So, these are things we can do on the landscape that help us move towards net zero, but really aren't carbon dioxide removal per se, but they're worth 7.6 gigatons per year. So about 33 gigatons or billion tons of carbon dioxide per year. So economic potential isn't technical potential. So what we could really do for a reasonable price, if you will, is not this 33 billion tons. So here's the kind of technical potential from a recent paper paper that's just going to come out by Stephanie Rowe and others, without BECCS, about these biomass energy, carbon capture and storage. They suggest the technical potential is about 30 gigatons of carbon dioxide per year, and that for $100 or about $1, 90 cents per gallon of gasoline, we could do about 11.9 gigatons through taking 11.9 gigatons out of the atmosphere. So we get maybe a third of that for $100 or less. Okay, so what's that mean? Global emissions are currently 36 billion tons. The global sink, that's for zero price. We're not paying for that right now. We already have a sink globally that's worth 3.6 gigatons of carbon dioxide per year. So 10% of our emissions is already sucked up by green stuff around the world, and that's free, right? Remember, that's 10%. So for $100, we can get this extra 11.9 gigatons. So in total, we can get 15.5 gigatons, and that's 43%. So we can think of that as saying that for $1 per gallon or 90 cents per gallon of gasoline, we could get 43% of our current world economy to net zero, which really isn't a bad thing if we really wanted to try to do it. Who's doing it? It turns out that because it's so low cost, everybody wants to do it now. This is the great thing. Practically every country now is signed up to be carbon neutral by some year in the future, 2030, 2050, you pick your year. And most of them are going to have to use some land-based thing, and many of them are actually already investing in land-based things. So, Amazon, Microsoft, Kroger, Danone, Cargill, all these companies are actually out there investing in soil carbon, trees, et cetera, right today to try to start moving their way towards, carbon neutrality or net zero. Is it possible to make such huge change on the landscape? Well, we already have. In the last 100 years, we've made an enormous change on the landscape. In fact, actually, the whole forest sector is actually carbon neutral over the last 100 years, and definitely in the last decade or two. So this right-hand side figure kind of shows emissions from deforestation on the top here, and regrowth in forests and green stuff around the world. And that regrowth in green stuff and forests has really outweighed deforestation emissions for about 50 to 60, maybe 70 years. And the net has been, carbon dioxide removal from the atmosphere. So in total, we've actually taken that's 800, think about that, 800 million hectares of land have been converted to agriculture, yet we still, in our forests, sucked as much carbon dioxide out of the atmosphere as we ever released from all that removal of land from forest into agriculture. That's a pretty phenomenal thing. These carbon gains are due to three things. Carbon fertilization is about 60% of it. So, unfortunately, as a result of our sticking carbon in the atmosphere, we're getting a benefit of sucking more carbon out of the atmosphere. Forest management's been a big chunk of that, actually. So about 30% of that gain down here is due to forest management, and 10% is due to policy, forest preserves, the things we're doing to try to, make our forests better as a society. Direct policy actions already reduced these net emissions by about 0.7 gigatons. So a lot of this actually in recent years is due to actual direct policies or efforts that we've made to actually make this sink bigger and to reduce this emission from deforestation. So it's kind of fascinating. We actually have made huge changes in the last century, and some of them have actually been good and have actually moved us towards net zero. The Brazilians, they're the ones who've maybe done the best. And the most obvious examples, they really reduced deforestation from about 1.8 million hectares per year before 2005 down to about 500,000 hectares per year. So it's ticked up in the last couple of years. This is a great example. It shows us that, societies can do this massive change in what's happening, and they can go backwards. They can backslide. Imagine that, I guess we've seen that pretty much everywhere nowadays, haven't we? Anyways, they've made a big change, and they've suggested that we could actually do this on a big scale if we wanted to. There are some huge challenges. Just talk about a few of them. Movement towards sustainable development goals may be more difficult with these land use options. I mean, if we want to move more land in the forest, food prices may go up. If we're going to store more carbon in the landscape, food prices may actually be higher. If we're going to take this biomass material and create energy out of it, and it's really a thing, and we can really stuff it underground, and it's really useful for us, yeah, biodiversity may be a bit in peril. That conditionality that Professor Socolow talked about, it's a real issue for us to worry about. And it's going to be a sort of a defining issue of the future era if we go this direction. Second, we need to mobilize $300 to $500 billion per year. I don't know about you, but that money's not just sitting around waiting to be used. You know, companies are investing in lots of things and they're not investing in this stuff. So there's a lot of money there. And you could think of it a different way. You know, that money's not coming out of governments, because I don't see any governments being willing to spend that much money. So if people aren't willing to spend it, then you can imagine all these other people out there who you want to do something different with their landscape. You know, they're going to have to give you $300 to $500 billion worth of effort for free. And that's an interesting question. Is anyone going to be willing to do that? So it's a big sort of money thing there. And the last thing is a money thing too. You know, large changes in how people will use land. It's going to require a big change in their livelihoods. Land is the fixed resource. With any of these options to go net zero, land becomes not infinitely, but a lot more valuable. So suddenly a resource that's already really valuable, especially in a place like Ohio, becomes a lot more valuable. And so we've already seen this play out when we talk about RED projects, that is reducing emissions from deforestation. Lots of people who are not so wealthy in many countries around the world are skeptical of these things because they know this stuff is valuable, yet they have insecure tenure to this stuff, this carbon, even to the land. Right. So this becomes even a bigger issue when this stuff is worth $300 to $500 extra billion per year. It's a massive challenge for us to deal with. There's some other challenges here. I'm not going to talk through these. These have been discussed to death in the sort of the circles of carbon sequestration and whatnot. Additionality, permanence, and leakage. You know, they're big problems. But however, there are now markets out there like the California carbon market where they've actually worked through a lot of these issues pretty effectively. So, you know, we can talk more about this maybe in the discussion. I don't want to talk through these because they've been widely discussed. They are important, but there are ways to deal with them. And they have actually been pretty well dealt with in sort of the markets that have evolved both in the US and elsewhere in other parts of the world. So I'll stop there. Thank you for your time.
Thanks, Brent. Next up, we're going to have Professor David Cole, who, in addition to giving his remarks right now, is my co-lead in the Sustainability Institute for our Sustainability and Sustainable Energy program. Dave, take it away.
I just share my screen, can I? That way. Actually, can you see that, Jeff? Can you guys see this?
Yep, you're good.
Okay, wonderful. All right, thanks so much. We'll go to slide mode here. I hope. Are we in slide mode? Yes, okay. So what I'm going to cover are some topical areas that have sort of been touched upon here and there throughout the course of today.
Actually, Dave, we still see your slide deck.
Oh. I'm sharing my screen.
There might be a button in the upper left that you can press to switch slide mode.
I'm not sure where to do that, actually. Sorry, upper. I'm fumbling. What's that?
Kind of. Now you should be able to switch.
So you guys can't see my slides? Is that the problem or not?
Now we can see your slides, but we can see the next slide too, if that's okay with you.
Oh, no. Okay, maybe that's, well, I'm not sure how to get rid of that actually. Yikes. Well, maybe that's okay. I don't want to waste time here. So let's just carry on. So what I'll try to touch upon are 3 or 4 topic areas that include air capture, which Rob talked about in his talk a little bit. I'll talk about this bioenergy vector, which also includes carbon capture and sequestration. We'll touch upon iron fertilization a little bit, and then we'll kind of end with some little bit of a discussion about what does sequestration really mean with respect to the subsurface. And so direct air capture is a really interesting one. It's starting to pick up some momentum. There's really a couple of different kinds of air capture. For those of you that haven't thought about this too much, there's passive versus active. They both involve different kinds of technology, membranes, sorbents. Some of them are chemical, some of them are solid materials. So this direct air capture with respect to storage, you can kind of see the example here in the lower left. This is a passive deep air direct air capture from mechanical trees. This is a technology that's been developed out of Arizona State. This is Klaus Lochner and the company that's sort of grabbed onto this. This is real interesting. Sort of, we're not moving fans. We're just letting air across these baffles, these 10-meter high trees. Actually, they're mechanical trees that he can sort of capture CO2 with. In contrast to some more conventional kinds of carbon capture, which you see on the right, which is actually an example from Climeworks in Iceland, which actually has fans. It's sort of sucking air across these fans, and they're capturing the CO2 either with some kind of hydroxide solution, or maybe it's a solid sorbent, which then they try to release the CO2, either to take the CO2 to products, or in the case of Iceland, they're actually injecting that CO2 into a geothermal system to sequester it, which is kind of cool. So the hope there is actually have permanence with respect to CO2 storage or sequestration. Globally, there's about, I think, 15 of these particular kinds of systems that are out there. They're kind of small scale. I think they're capturing about 9,000 tons of CO2 right now, which is actually a very, very small quantity. The hope is to take this to 10 megatons, or millions of tons rather, over the next decade or so. This is expensive technology, but doesn't have a very big land footprint, nor does it have a very big water footprint. So it's actually a pretty interesting technology that's starting to emerge, but it's obviously not there yet. And so in terms of life cycle, you kind of see on the right, you take in the CO2 from atmosphere. We either can inject it into the subsurface, or we can use it to enhance oil recovery, which actually begs the question, is this really getting us into negative or zero emission or zero impact kind of space? Not exactly. On the right, you kind of see this actually more magnified in the sense to take the captured CO2 and make a synfuel out of it, which also requires some sort of renewable energy input and water. But then, of course, burning that fuel then returns CO2 to the atmosphere, or we can use it in various ways, right? So again, there's this life cycle, which has different rates, obviously. And so we have to be kind of worried about what those rates are with respect to uptake and then release within the context of humankind and time dimension. That's important to us. Bioenergy has been talked about some already. Again, this is a really simple kind of a slide. For those who don't appreciate this, this is a renewable energy source. But the issue there is long-term versus the short-term benefits. There's so many different ways you can capture energy from crop waste, forest residues, and so on, woody plants, microalgae, and whatever, even food waste, which we actually, I think, do at our Blackwell Inn on campus. I think they actually capture that food waste and reuse it. The problem is we're producing products that actually then release CO2 back into the atmosphere, like biogas, alcohol, depending on how they're used, biodiesel. So you can kind of see that cycle, that life cycle there, a cartoon on the right. If we can take that CO2 to products, which sequester there, we can take that CO2 to the subsurface. Of course, that's a better option. And so what we're talking about is a life cycle and this difference in rate. In the short term, we're actually returning CO2 to the atmosphere, but over long term, if we can actually enhance plant growth and expand the use of these various waste products, and perhaps we can get a handle on, again, controlling that sort of mass balance of CO2 that we see in the atmosphere. And so in terms of the US, it's interesting to note that this is data from 2019 as reported in 2020 rather, by the EIA. A good fraction of the renewables in the US are actually biomass based, okay? And so roughly 40-some%. Obviously, hydroelectric is a big contributor, and we know that wind and solar are picking up momentum in terms of their use, both globally as well as in the US and even in the state of Ohio. But it's interesting to note that biomass really still dominates what EIA is calling renewable, okay? So that's kind of interesting. And so, thinking about Ohio, we've seen this map a couple times showing the distribution of different kinds of energy vectors. As we noted, as I think Daniel noted, we have wind kind of in the northwest. If you kind of look at the biomass distribution, which is these green buttons, most of these guys are also up in this sort of northwestern quadrant, northwestern side of Ohio. We have the hydroelectric along the Ohio River. So this distribution is also kind of interesting in terms of the demographic area that we're actually impacting. But it's also good to note that there are a number of biomass power plants that have popped up in Ohio in the last few years. So we're making, progress bit by bit, which I thought was good to highlight. Okay, so ocean engineering, this is one that many of you may have not even thought about or heard about. So it's kind of interesting. It's really fairly novel, but also at its very infancy. The idea here is to fertilize the ocean to get sort of expanded phytoplankton growth. Of course, photosynthesis is our friend, as we just heard in the previous talk. If we can get, plants or phytoplankton, algae to take up CO2 and produce oxygen, this is a good thing. So there's been a number of experiments run where people have actually seeded the ocean with iron sulfate to kind of take advantage of areas where there's actually high nutrient but low chlorophyll regions where we can enhance that phytoplankton growth. And so roughly 1 kilogram of iron can yield about 10 to the 5th kilograms of phytoplankton, which in turn can take up CO2 and produce oxygen. Of course, there's all sorts of issues associated with this in terms of impacts on ecosystems. Red tides, algae, if we come in contact, can be toxic. It can generate O2 depletion zones. We see these O2 depletion zones in Lake Erie. We see them along the Gulf Coast, and also can lead to deep water acidification, which is an issue. Interestingly, nature runs this experiment. When volcanoes erupt, if there's enough iron content in that dust and there's enough of a volume of the volcanic ash, then it can seed the ocean. And so this happened in 1991 with Mount Pinatubo in the Philippines, added about 40,000 tons of iron-rich dust. We actually saw a kind of a slight drop in CO2 and a slight increase in O2 during that time. The particulate that was distributed by Mount Pinatubo also affected sunlight, and we also had some cooling globally. So really interesting and natural experiment. Of course, we can't engineer those and we can't control them, but nature does do this. So we do have a model from which we can base our future geoengineering on. And then there's also chemical weathering, which is an interesting one as well. I mean, nature does this. Nature weathers rock. It produces, carbonated surfaces. And in fact, currently, I think there's about 1.1 billion tons of CO2 get sort of sequestered from natural weathering globally. And the thought is if we could enhance that by using the right kind of rock and the right kind of scenario, we might actually be able to increase that to 5 billion tons. And if we use a certain really iron-rich rock, if we can get enough of it and get enough of it in terms of its surface area, engineered-wise, we could actually sequester close to 90-some billion tons of CO2. Okay, so it's actually could be a pretty big deal. The problem is it's expensive. You can see the flow diagram at the bottom. We have to move material around. We have to actually get the right kind of iron-rich material, iron, magnesium, calcium-rich material to a place where we can actually expose it to CO2 and water. But nature does this. So you can kind of see over on the left a couple of examples of waste slag and landfill locations in the UK where you actually make carbonate rock basically at the surface. So again, we're trying to learn from Earth. We're doing geomimicry, if you will, and Earth is pretty efficient at doing this in some sense. So maybe this is something we should think a bit more about. And there are some projects afoot that are being kind of developed to kind of get into this game. There was a lot of talk about storage. We heard about CCS a lot. So I thought it would be good to flash up this slide to just show you what are we talking about here. We're talking about putting CO2 at depth, so it's supercritical, so deep enough so where we can actually occupy pore space in different kinds of geologic environments. They may be saline aquifers, it may be a depleted oil or gas reservoir, or maybe to help enhance oil recovery or gas recovery, which of course by itself is not helpful because we're still going to use oil and gas to produce carbon. But there's a lot of activity globally looking at subsurface storage of CO2, both on the terrestrial as well as in the marine environment. Best example is Sleipner off of Norway, which has been running for over a decade. They've been putting about 1 million tons of CO2 into the Utsira Formation every year. So there are experiments running to do this. Of course, there are problems. How to predict, what's happening, how to ensure, permanence. The risk assessment issue is particularly important. And also NIMBY, people acceptance for this, not in my backyard, for example, is also a potential problem. And so we've had that issue in Ohio. I think Rob mentioned the Mountaineer project. Well, that had geologic issues, which is why that failed. But then we had the Burger plant, which also was one that did not work in Ohio, largely because the public did not accept that project. And so there was pushback. Okay, so we get this, right? This can happen. And I thought I would kind of close with this slide. I wasn't going to show this, but I thought there was issues of flaring and all these different things in this life cycle. So what you see here are two flow paths. They're somewhat different. Again, we're using gas here, but think about this. So the one on the right showing gas from flaring into agriculture under glass. We could be producing power through combined heat and power. We recycle the CO2 back into the large, these very large, expansive greenhouses to help promote growth. And the excess methane we could send, in this case, this happens actually in Illinois and Indiana. This is actually happening now to the Chicago City Exchange. But we can also do modular methanol production. We can also do hydrogen generation. And similarly, we can take existing oil and gas or gas combined heat and power. We can run modular desalination, and we can also do growth under glass again and use that CO2 to recycle into greenhouses. So this is really interesting kind of combination of integrated technologies based on gas, but still trying to keep that carbon footprint either low or maybe even negative, depending on how well we use the CO2 within the ag part of this kind of flow. So that's it for me, Jeff. I'm not going to go on. This kind of brings up to a close for me.
Great, thanks, Dave. Professor Robin Wilson is up next. Robin, take it away.
Thanks. Hi, everybody. Let me know if you see my slides. I think I'm sharing.
Yep.
Good? Okay, great. Well, thanks for having me. I am a behavioral scientist, and I study how individuals make decisions under risk and uncertainty. And a lot of my work has started to focus on climate adaptation and how individuals, homeowners, landowners, as I'll talk about today, are making decisions about how to navigate the risks that are posed by climate exacerbated hazards. So I was invited in this kind of group of thinking about sequestration, kind of going back, I think, to some of Brent's comments about the potential in agricultural landscapes for sequestering carbon and having other potential climate benefits, but also adaptation benefits, which is the space that I typically work in. So I'll just be talking a little bit about kind of what we know about the potential for that in this space in terms of farmer decision-making and some ideas that I have based on some of our empirical studies on solutions we might be able to engage in. So for those that aren't super familiar, I just wanted to give a little recap of kind of agricultural land in the US. So this map is just showing what percent of the landscape across the US is in agriculture. Darkest green is 90% or more. So you can see the kind of breadbasket, I guess, if you will, up the middle of the United States that's heavily agricultural. But in general, it's about 44% of US land that's in agricultural production. That's about 1 billion acres. And that's been declining since the end of World War II from a high of about 63%, largely due to urbanization. But it's only 1.3% of the US population who's making decisions on these landscapes. So it's just about 2.6 million people who are farmers and actively engage in land management decisions in this space. And this has also been on the decline since the turn of the last century from about 40%. So really small part of the population when we talk about decision-making and human behavior, but big land mass in terms of its potential impact. Also, there's about 2 million farms in the US. Again, this is a decline from about the 30s of around 7 million, but the average farm size is increasing. So the average farm size now is about 450 acres. Obviously, there are some massive farms in there that aren't really reflected in that figure, tens of thousands of acres. But the average farm size, at the turn of the last century was only 150. So farms are getting bigger. The number of farmers are getting smaller. The overall land mass is getting a little bit smaller. But these are just some of the dynamics just to kind of set the stage for what we're talking about here. And interestingly, for those who've been following what the current administration is interested in, and part of their, and maybe this was talked about today, I missed the beginning of the symposium due to teaching, but an executive order that came out recently from the Biden administration talks about empowering workers by advancing conservation, agriculture, and reforestation. So I don't know if that's been talked about, but clearly there's a pivot in this administration right now to thinking a lot more about these issues. And specifically within that executive order, there's talk about America's farmers, ranchers, and landowners and the important role that they play. And this goal has been put out there of conserving at least 30% of our lands and waters by 2030. So ensuring that, in this case, the land base is in conservation practices. And so unless we create a lot of new national parks and other sorts of things, one way to get to this goal is through increasing conservation on those working agricultural lands. And specifically, this is what I like as a behavioral science, the executive order says, how do we use existing programs and encourage the voluntary adoption of climate smart agricultural practices? So this is against this bigger landscape of the reality that the way we kind of manage agricultural lands in terms of conservation decisions is through voluntary programs. There's really no regulatory structure outside of some examples within particular states like California and Florida. But at a federal level, we're talking about these voluntary, often incentive-based programs trying to get farmers to engage in these practices. So what do we know about why farmers, sorry, typo there, do or do not engage in some of what we might think of as soil health practices? When we talk about the potential for sequestering carbon across working landscapes, we're often talking about improving soil health, engaging in practices that are going to ensure a continuous living cover on that landscape and less disturbance of that soil, as an example. So two of the ways we might think about this on the majority of our agricultural lands are through cover crops and through limited tillage in those systems. So on the left, you just see an example of cover crops growing in an agricultural field. You can see the stubble left over from the corn that was harvested, and the green that you see are the winter cover crops that are planted at the end of harvest and are there, again, to retain nutrients, to directly retain soil and prevent erosion, but also over time improve soil health and have other benefits to the landscape as well. And then there's also on the right here an example. This is actually of strip tillage, but instead of engaging in conventional tillage practices where the soil is heavily disturbed, one option is no-till, where you don't disturb the soil at all. Another is strip till for farmers who feel like there still needs to be that piece of it. And there are benefits to strip tillage for water quality as well in terms of how we apply nutrients to the landscape. So here's an example of a field where you can see most of that field has not been tilled up. You see that stubble left over from the corn, but you see these strips where it has been tilled for planting and again, also for nutrient application. So those are two practices that I've focused on a lot in my work. Again, not necessarily motivated by a focus on climate mitigation, more as a focus on climate adaptation and dealing with the fact that it's getting warmer and wetter in a lot of these regions and in our region in particular. And one way to deal with that is improving soil health. But interestingly, these are a set of practices that have both great adaptation benefits and great mitigation benefits. And so what we've been looking at in our studies is trying to understand who's doing these practices, who's not, why does that gap exist? How can we design programs and policies to better engage these farmers? And so what you see here is just an example from a panel study that we did from 2016 to 2018. Over here on the y-axis, you see the % of farmers reporting being in each of these categories. The dark gray are farmers who reported using a practice at a particular point in time. The lighter gray are those who said, I'm not using it, but I intend to use it next year. So these were people kind of reporting on their future behavioral intentions. And I also want to point out here, just to be clear about the numbers, this is representing the % of farmers or operations that are using the practice, not the % of land in that practice. So for instance, cover crops, although we see here that almost 30% of farmers, and this was in the Western Lake Erie Basin, are reporting using cover crops, most of them are only using cover crops on less than a quarter of their land. So when you look at the total land base in cover crops across the US, it's 5% or less, I think. It ranges, some places it's worse, some places it's better, but it's pretty small. So we have a long ways to go. And tillage is a little better, but by no means is a majority of the landscape in any form of limited tillage, whether that's no-till or strip-till or anything. And so what we see here is that of the farmers in our population, about 30% reported using cover crops, a little bit more reported using a form of subsurface placement of fertilizer, which again is limited disturbance of the soil. But what you see in the gray is a pretty large group of people who say they aren't doing it, but they're planning on doing it in the future. So from a behavioral standpoint, we would say these are the people who can be convinced to do it. So there's about 30 to 40% of our farm operators in this area who we think could be convinced to engage in these practices. They're interested, they're motivated, they haven't found a way to do it yet. Whereas those who are left over in this calculation, that something about 30 to 40%, I guess, are folks who we wouldn't imagine would be interested in adopting these practices until they become much more the status quo or the norm within their communities. So we often collect data through survey mechanisms, other sorts of methodologies, but essentially try to statistically model what the likelihood is of someone having a particular practice in place, given a set of farmer characteristics, given a set of farm characteristics, given certain beliefs that they have. And what we see time and time again in this work is that the likelihood of someone having these two particular practices in place, but this also holds true for others we've looked at in the conservation space, that likelihood goes up as the farmer's perception of the practice feasibility increases and their perception of the practice effectiveness increases. And in fact, we've seen that farmers with kind of high, so imagine a scale of 0 to 10 measuring this construct of kind of how feasible or effective you think a practice is. Farmers who have a high level, which is like around an 8 out of 10, versus those who have a low, which is about a 3 out of 10. As you go from low to high, those farmers are 10 to 15 times more likely to already have these practices in place. So we see this really strong effect of the more feasible it is for you, given your operation, the more effective you believe it to be, the more likely you are to have it in place. And so what does this mean for kind of engaging farmers in this space? You know, from a behavioral standpoint, this points to a challenge of increasing feasibility and increasing the effectiveness that farmers believe these practices might have at solving problems, whether that problem is climate change, whether it's soil erosion, whether it's water quality. You can frame it in a lot of ways, but until they're convinced they can do these things and that they will effectively solve a problem of interest, they're not going to be doing it. So one way we can think about engaging them to do more of these practices is to work within the system. So this is recognizing that we have a certain set of policies. We have a federal system that I would argue is broken when it comes to agriculture and food, and probably to climate policy too. But we might have to work within that system in the short term. And so we might need to address kind of rented acreage issues or landlord agreements. We might have to go beyond the farm operator and recognize that also over half of our ag land is actually rented from a landowner to a tenant. And so if we want to make better progress in these sorts of practices on ag land, we may need to focus more on the landowner and less on the operator when that land is actually owned by someone who's not daily engaged in the management of it. We might need to provide more tailored recommendations. So we see a lot of farmers not convinced that what we're suggesting will work for them. And they may need more of that technical support to kind of think through, how can this work for you? How do we make this feasible on your operation? How do we ensure it's effective given the sorts of constraints you're working with? And the economists, I think, will love this, but conduct better cost benefit analyses. We still don't do a great job of communicating the economic benefits of some of these practices. So it's all well and good to engage in pro-social behaviors and to help solve climate change problems, but unless we can show what those on-farm or on-field benefits are of these practices, like how improved soil health can lead to some economic returns, farmers will be hesitant to engage in these things. But I want to end with just this kind of pitch for redesigning systems. So again, I think a lot of people would argue is that we could make progress within these systems, but we also might need to rethink how we engage farmers and landowners in this space. One radical idea is to do away with government subsidies. So right now, the farms are highly subsidized under conditions of extreme weather, under the economic conditions that were faced last year in agriculture. And there are places where farmers are not subsidized and they have to invest in private insurance. They have to engage in conservation as a way of mitigating their own risk, such as in Australia, South Africa. So there are examples of people doing this. We happen to not be one, nor is Europe a good example. Maybe if we're going to keep subsidizing ag, we need to tie those government subsidies to conservation action. So I had a farmer call me the other day and basically complain about how he was getting a payout of $90 an acre through some federal programs for weather and economic related disaster. And he said, with no strings attached. And he was amazed that the government would just hand out this money and not ask for something in return. So maybe one way to make better progress here is to say, okay, we'll bail you out when these things happen, but if you want that to happen, here's what comes with it. And then perhaps the least controversial of these three suggestions is to design more thoughtful incentive programs. So we have a lot of standard programs that have been around for a long time that are not necessarily as motivating to farmers as we would like them to be. And so maybe they need to be more thoughtful. And one that I've talked about with folks before is we often talk about taking land out of production and putting it into conservation. So retiring land from agricultural production and putting it in, say, a conservation reserve program. What I think is interesting about that is that land is still producing, it's just producing a different set of services, right? We've removed it from producing food or in the case of the Midwest, feed and fuel really, into producing other services that are also very important, but not valued appropriately in our economic systems. So perhaps our systems could work, but we need to think more carefully about the value of what that land is providing outside of its traditional approaches. So I will end with that. Thanks to the funders and the farmers and the collaborators on this work.
Great, thank you, Robin. We have 5 minutes for a discussion before we will move into our next session on social and community. One of the nice things about doing this from home is you get to see my cat. So we've had a number of questions in the Q&A. One that is specifically highlighted for Dave about the alum cycle. And I also want to bring up a question about where did that question go? About how we feel about corporate commitments to net zero carbon. So again, we now have 4 minutes. Dave, the alum cycle.
Well, unfortunately, I'm not that familiar with it. I saw the message come in from Jory, so I need to know about this. I was under the impression, this is probably something new. I was under the impression that the real bona fide CCS plant in the U.S. in Texas actually was closing. So I'm not sure which one he's referring to actually. So I feel a little sheepish about that. I mean, and of course, carbon capture is in the eye of the beholder in terms of the methodology, right? So, and also the kind of plant that we're getting CO2 from, whether it's an industrial chemical plant or whether it's a real power plant. So I apologize to Jory. I'll need to kind of connect with him and figure out exactly what this particular facility does. It looks encouraging, but I'm just not familiar with it. So I'll just leave it at that.
Yeah, no worries, Dave. There's actually another question that just came in that I will use to preempt the corporate question. The question is, can we improve the ecological integrity or completeness of conservation reserve lands?
That sounds like a Robin question, but
yeah, I'm not sure if I understand the question. Can we improve the ecological integrity? I guess I'd want to hear a little bit more. I'd be happy to dialogue through the Q&A box about that offline as well. But yeah, I'm not sure if I understand the question.
Well, I can certainly comment on it. There is, an ecological index for assigning which land gets brought into the conservation reserve program. And it can certainly be improved. That's definitely for sure. I mean, the metrics we use for that aren't great. And they don't include carbon at the moment. So that's something that could definitely be improved.
I'll just make a quick comment that when I was looking into chemical weathering, one of the things that they discussed was using some of these iron-rich, materials to mix in with soil and farming that get carbonated due to CO2 uptake and weathering, but also release nutrients during that alteration reaction to the soil, to the farmland. So I'm not sure if that falls within this category of ecological enhancement or not, but certainly the CCS, one CCS vector is if we make these carbonates at the surface, say in a processing sort of flow stream kind of context, we can add these to soils to do soil amendments to combat acid soil. This is something that people have talked a lot about. So those are two possible vectors that might lead to some enhancement, I suppose, in quote unquote the ecosystem response, perhaps.
Great. I want to also provide the opportunity for Brent, do you have, so you talked about a lot of these ecological approaches and Robin talked about behavior around these ecological approaches. Do you have anything else that you might want to build off of what she said? Maybe another question earlier was about market mechanisms. What do you think?
Well, I think that there, we're, the market for carbon, there is a market for carbon out there now, and it's building and growing. And this is something that's just going to keep growing as corporate commitments continue to grow, right? So, we're seeing big investments. I mean, Microsoft and Amazon are investing in forest land right now and are investing through other companies like Nori and Indigo Ag on agricultural land. So this is happening as we speak, and farmers, foresters are being contracted for the carbon on their landscape. So the reality is it's happening, and it's almost happening so fast that, you know, policymakers are kind of caught off guard because EPA doesn't have any good rules for it. USDA doesn't have, you know, USDA, you know, there was a law that was put in front of Congress. I forget who brought it up, but they put it in front of Congress last fall to try to have USDA start to arbitrate some rules for doing this. You know, these questions of additionality are really, really important. If you look at the, and we're doing a new nationally determined contribution for the Paris Agreement, and in the last nationally determined contribution, forests were 25% of the goal of 25% reduction in carbon emissions by 2025. So that was for free. That was, you know, that was not additional carbon, but for free, foresters and landowners were giving that carbon away, and this included agriculture as well, to the US government to make a commitment to the rest of the world to not have as strong of reductions by the energy sector, right? So we actually, that actually was happening and will happen again. So this is really a huge area for, I think, you know, research by all kinds of people. And, you know, to Robin's point, I mean, this can become a massive issue for landowners. I mean, imagine you're a landowner who signs a contract today for, you know, $5 carbon or $6 a ton for carbon, only to find out, you know, 5 years from now, that stuff is actually worth $30 a ton. I mean, how upset are you going to be when you've got a 15-year contract for this stuff and somebody else is getting paid a bigger number? You know, so this is going to just keep exploding as far as I can tell, largely because of sort of the policy changes at the federal level.
Yeah, these are important considerations. Move on, though, there is a clarification in the Q&A. So maybe Brent and Robin, if you two could take a look at that while we move on to the next session. Thank you, Robin. Thank you, Brent. Thank you, Dave. We're going to move on to the session Power to, for, and from the people, which is very much focused on social and community issues and considerations with the energy system. A number of issues came up earlier today with Professor Socolow's keynote and in other follow-on comments about the just transition and the engagement and effects on people. So we have Professor Anna Willow here, who is an anthropologist who studies a lot of ways in which people and communities are affected. Jeffrey Jaquette will rejoin us from earlier. And we also have Myra Moss from Ohio State Extension. Anna.
Great. So would you like me to go ahead and go first? Because on the list I'm last, but I'm happy to go ahead and do it now.
Yeah, go ahead, go first. I already called you out.
Okay. Yeah, I think in this case, it doesn't really matter which order we have things. All right, so you should be able to see my screen at this point. Please do let me know if that is not the case. So thank you so much for having me. I'm going to talk briefly today about the problem of extractivism and how we can move toward a just decarbonization. In his introduction to Noam Chomsky and Robert Pollan's recent book on the climate crisis, political economist C.J. Polychronou claims that climate change is probably the greatest existential threat that humanity has ever faced. Well, I can't disagree. I also can't help but think about the larger, more abstract forces that underlie both the climate crisis and many of the other socio-ecological systemic crises we face. When we consider the causes of the climate change and the causes of inequity within and between world regions, it quickly becomes apparent that the roots of these problems are tightly intertwined. That our relationships to the planet we rely on are as broken as our relationships to one another indicates that our culture may be the biggest crisis of all. We know we need to rapidly reduce our rate of greenhouse gas emissions if we're to have even a chance at averting widespread global climate catastrophe. And even in the best case scenario, the stable climate of the Holocene is a thing of the past. And even with the hope of a new federal administration, this is a monumental task. It's a task that can feel insurmountable given the current state of affairs and all we need to overcome. And yet, decarbonization is not all that we need to do. We also need to ensure that decarbonization is accompanied by the creation of more equitable, democratic, and sustainable social institutions in the US and beyond. So we have hard work ahead of us. Some people might say that the need to tackle multiple concurrent problems makes the path forward more difficult, but I don't think so. From my perspective as an environmental anthropologist, I see the conjoined nature of these challenges as a call for a profound shift in our paradigm. Increasingly, we're coming to understand that our conjoined crises will only be resolved successfully and durably when they are resolved together. We don't just need new renewable energy and clean transportation technology. We need a whole new set of values, a whole new way of life. So I'm going to introduce one small piece of this larger struggle today, one aspect of Western industrial culture that I see as in desperate need of revision. In my recent work, I've used the term extractivism to help come to terms with what ails us. I define extractivism as a mindset and a pattern of resource procurement based on removing as much material as possible for as much profit as possible. Key here is the idea that extractivism is more than just a way of using the earth and its resources. Extractivism is also a way of thinking. It's a way of being in the world, a way of positioning ourselves in relation to the natural realms that we occupy. So therefore, it's not just and not primarily an environmental problem. It's also profoundly political, social, cultural, and economic. Extractivism often appears in obvious places. Mineral and coal mining, oil and natural gas production, all show us extractivism in action. But it is also seen where forests are clear-cut, where massive hydroelectric dams tap the energy of falling water, and where industrial monocrops strip the soil of its fertility. And when we remind ourselves that extractivism isn't just a physical process, but also a way of thinking that drives these processes, we also start to see extractivism in other places, where the environment is used as a sink for polluting byproducts, where human labor is inadequately compensated. Numerous inequities can be examined through this lens, and even on a personal level, I think human relationships at times reproduce the extractivist dynamic, with one party extracting as much time, energy, and attention as possible from the other. These unhealthy relationships mirror the inherently inequitable relationships between Western industrial culture and the non-human world. Although international leaders have voiced support for environmental integrity as a fundamental human right, the global, regional, and local distribution of benefits and harms associated with industrial production remains as inequitable as ever, with violations of supposedly inalienable rights taking place throughout the global South, as well as among poor, minority, and indigenous populations in the North. A disproportionate amount of extreme extraction of hydrocarbons, as well as other resources, proceeds on the lands of indigenous and other marginalized peoples without their full and informed consent. Natural resource extraction and social exploitation go hand in hand. Thus, although they are commonly discussed as distinct subjects, environmental degradation and human rights abuses are inextricably entangled. For indigenous peoples who make their living from the land and feel a deep connection to ancestral homelands, extractivism has become a matter of cultural genocide, many say. Increasingly, the victims of extractivism are fighting back, and extractivism is being answered by activism. In my 2018 book on the topic, I used the textual formulation extractivism to underscore the fact that extractivism does not proceed uncontested. Extractivism means taking action to counter extractivist development and denomination. Everywhere extractive industry operates is someone's home. Regions sacrificed in the name of extraction are almost always already inhabited, utilized, and valued in ways that are largely incompatible with the extensive environmental transformations that extractivism implies. Whether residents' claims to lands and resources are misunderstood or simply dismissed, externally imposed extractive schemes disrupt subsistence economies, jeopardize affirmative place-based identities, and hinder communities' capacity to function as effective, independent entities. For these reasons, extractivist projects are often perceived as attacks and are often met with defensive resistance. Conflicts between those intent on profiting from the removal of resources and those determined to protect their lands and lives have been frequent and fierce. For extraction zone residents everywhere, challenging industrial encroachment is seen as a necessary struggle for survival. And we see this dynamic all over the world. From the Hopi and Navajo lands of the American Southwest, where indigenous communities have witnessed the mining of Black Mesa and the consequent depletion of the Navajo aquifer, to the strip mined landscapes of the Northern Cheyenne homeland and the massive mine mouth power plants that degrade air quality on the plains in order to power the Northwest, to the removed mountaintops of rural low-income Appalachia, and over oceans where vast surface mines overtake Adivasi tribal communities in India's eastern interior. From the destroyed boreal forests of northern Alberta, where Cree and Métis communities suffer from lost subsistence livelihoods and pollution-driven health impacts because of what has been called the most destructive project on Earth, the tar sands, which cover over 50,000 square miles, to the Niger Delta, where oil extraction stands synonymous with human rights abuse, and home again to communities where shale energy extraction proceeds in the literal backyards of Ohioans who fear for their health and safety. So these examples that I've just shown at lightning speed highlight coal, oil, and natural gas as extractivist industries. And while they might be upsetting for people who are concerned about environmental injustice, they're probably not that surprising. But extractivism is also unfolding in places in ways that is more likely to give many of us pause. Numerous hydroelectric projects are being constructed around the world, and often these are touted as clean, green solutions to carbon emissions and climate change. Recent research has shown that hydroelectric reservoirs can in fact be significant sources of greenhouse gases, but even beyond that, they too often proceed in ways that are deeply unjust and are socially unsustainable. The Belo Monte Dam in Brazil and the Site C Dam in northeastern British Columbia, Canada, are just a couple striking cases in point. Thousands of miles apart, vast indigenous homelands are being flooded despite the vehement protest of residents to benefit more powerful people and industries elsewhere. Wind energy too, so often taken as a symbol of life beyond fossil fuels, cannot be disentangled from injustice. Mexico's Isthmus of Tehuantepec is one of the windiest places in the world. Over the past decades, developers have rushed to take advantage of the wind, turning the elusive movements of air into a resource amenable to possession and profit. With the exception of a few well-to-do landowners, local people oppose these developments. Worries about damage to local ecosystems, especially the fisheries that support the livelihoods of indigenous Wave citizens, and the fact that wind energy does not power local homes, but is instead transmitted to faraway corporations eager to offset their energy costs and environmental impacts, are at the forefront in their minds. Offering local people little and proceeding without their participation, a majority of Isthmus dwellers identify wind development as an inequitable imposition. That they should be the ones required to bear the burdens of climate change mitigation strikes many poor people as absurd and unreasonable. Solar impositions have generated similar stories in Greece and elsewhere. It's possible these stories show us to decarbonize in a way that is still extractivist and unjust. Even while standing as symbols of sustainability, solar and wind energy could ultimately reproduce the problematic politics and the unfair impacts that we have come to associate with dirty fossil fuels and destructive clear cuts. Renewable energy could defeat fossil fuel addiction, but still leave the extractivist outlook that produced it intact. The renewables revolution is positive and it's necessary, but it's not a panacea. As I see it, overcoming extractivism is a grand challenge of our time. As I stated earlier, we need to do more than simply find new ways to produce energy. We need to fundamentally transform our societal structures and our expectations. Moving beyond extractivism will require renewable energy sources that develop in environmentally and socially responsible ways. It may very well mean smaller scale, more dispersed production with shorter supply chains and greater self-determination. But most importantly, it will mean changing how we think. We need to recognize that we're part of the natural world, neither apart from nor above it. Human societies and economies cannot continue in the absence of functioning ecosystems. This is obvious for the people who support themselves through direct interaction with the environment, but it's equally true for those of us who experience the inevitabilities of ecology more indirectly. If humans damage the environment so much that we can no longer sustain ourselves, everything we have built will come crashing down. Growth, we need to realize, isn't always good. Bigger isn't better. In the modern era, it's been widely assumed that using more energy implies affluence. but a lifestyle that demands the annual equivalent of over 13 barrels of oil per person is indefensible in the long run. Taking more than our rightful share of the Earth's finite resources is a spectacle of short-term selfish thinking. It can't continue. Excess, we must understand, does not equal success. We need better ways to measure our worth. The dream of perpetually increasing material abundance is no longer tenable. As Canadian anti-tar sands activist Tony Clark sees it, either we start changing the dream and charting our transition to a sustainable future, or we will surely perish as a people, as a civilization, and perhaps as a species on this planet. We need to stop competing with neighbors, friends, and family members over who has the biggest house, shiniest pickup truck, and greenest lawn today. We can strive instead for equality among neighbors, neighborhoods, and nations. We can learn to live well rather than living for more. Other, more meaningful quests can guide our ambitions. Who do we make happy? How do we contribute? How do we make our world a better place? It's easy to be pessimistic about whether such changes could ever occur, but anthropology, my field, has taught me and compels me to tell you that other ways of life have always existed in other times and places. Extractivism is an attribute of culture. Like other cultural attributes, it is particular to a given time and place. This means that it's not universal, hasn't always been with us, and can be changed. It implies that we have other options for crafting a healthier and more sustainable relationship with the non-human world and with one another. This is the source of my hope for the world. Extractivism is not an eternal or inherent part of who we are as human beings. We can live differently. We can do better. Thanks. I will stop my share now. That's it. Hopefully lots
That
to
was
talk about,
fantastic.
more of a reflection and thoughts than facts and figures.
Sure, that was fantastic, Anna. Great. We will move on to Professor Jeffrey Jaquette, and I'm sure we'll have a great discussion after he and Myra Moss go. Jeffrey, go ahead.
Thanks, Jeff. Hopefully you can see my screen here. I think this talk will follow nicely Anna's talk. Just sort of meant to be sort of a broad level talk about the issues related to wind energy, as Jeff had asked me to talk about. And that's what I'm going to do. Let's see. Yeah, just a couple, speaking of facts and figures, just a couple of facts. You know, we have more than 60,000 wind turbines in operation in the United States now, mostly built in the last 15 years. I'd say even mostly built in the last 10 years, second only to China in terms of the number of wind turbines that we have. You could say it's a remarkable achievement. It's one of the fastest growing industries sort of on record when you think about the number of sites. 60,000 of them, yet it's only 8% of our electricity production, roughly speaking. So, you know, just doing some simple math, if we want to get wind to be 16%, that would require 120 wind turbines. If we want 23%, that would require 240,000 turbines. So this 60,000 is just sort of the tip of the iceberg. And there's might be some other ways of getting at this.
It appears as though we've lost Professor Jaquette. Myra, are you able to fill in while Jeffrey reconnects?
Yes, I can do that. Let me turn my video on. Okay.
So again, here we have Myra Moss, who is a professor with OSU Extension, and we figured that we would make sure that we talk about what's going on in Ohio, and clearly Myra can inform that.
Okay, great. Thanks very much. My presentation is more from the grassroots level, actually working with communities and individuals in Appalachian Ohio and also in Western Ohio and Southern Ohio, where large scale solar and wind is happening, and also obviously where shale oil and gas is happening. So briefly, what extension is we're located in each of the land-grant universities. We have 4 program areas. They are 4-H youth development, family and consumer sciences, ag and natural resources, and community development. And I'm going to focus in on those last 2 because those are the ones that really have been most involved with shale development in Eastern Ohio, and also with wind and solar. Okay, so the title of this panel was Power to the People. And my way of looking at this is if knowledge is power, which I believe it is, then extension provides power to the people, just maybe not quite the way we're looking at it through other presentations. Extension's role is to provide and impart information, education to individuals and communities, specifically so they can build capacity in order to make informed decisions about issues that impact their lives and affect their livelihoods and their quality of life. So that's basically what Extension's role is. And the way we do that is through various methods, variety of methods. One-on-one interaction, we'll sit at people's kitchen tables and talk to them. Workshops, facilitated meetings, we'll bring in experts. And then we also have written fact sheets, bulletins, and other educational materials. And then a lot of what we do also is taking what our experience is in the field and sharing it with our colleagues throughout the United States. So we do basically applied research and case studies. So one of the major things, obviously, we've been involved with since about 2010 is shale and oil gas development in Eastern Ohio. And to kind of set the context, because I've been involved in this part of Ohio for many years, both with Extension and before Extension. And Appalachian Ohio basically has a natural resource-based economy. As we probably all know, coal was a huge driver of the local economy years ago. And then that transitioned, basically went away. The high sulfur coal in Ohio was replaced with lower sulfur coal from the West. So that industry went out. A lot of people lost their jobs and they never recovered. So Appalachian Ohio is very economically distressed. Now, what brought them out of that distress was the shale oil and gas boom and the impact that it had on the local economy in terms of creating jobs, in terms of bringing money into the local communities. So it was a boon for for that part of the state. In 2010, things really got going, although we have colleagues in Pennsylvania who were affected starting in 2005, but it really didn't hit Ohio until 2010. And it was kind of not on the, how can I put it? It was below the radar in a sense. The way we knew it was coming was people with laptops showed up at our county courthouses and started to look for property owners, and then approached those property owners and tried to get leases with them for their oil and gas reserves. So it was kind of quiet. They didn't come in and talk to any local leaders until well into the process. So people were kind of frightened, as you can well imagine. What's going on? What is this hydraulic fracturing and horizontal drilling all about? So we really ramped up our programs beginning in 2010 and started out with what is hydraulic fracturing and horizontal drilling, and what kinds of impacts can you expect as a landowner? How does your community need to be prepared for this? We worked an awful lot with local leaders, and then also incorporated our sustainable planning approaches to try to help communities prepare for what was going to happen. So between 2010 and 2020, we conducted 250 public meetings with over 18,000 people attending. And as you can imagine, some of these were very heated. I talked to a colleague yesterday who said he remembered the police being called to one. So they were kind of all over the board. To be honest, we did not see a huge amount of pushback because people were so hungry for any economic opportunity that this seemed to be a good fit. Also, Appalachian Ohio has a history of natural resource extraction. So with oil wells and coal mining, it did not seem to be that big an issue. Now, our programming with the communities evolved as the issues evolved. So we start out with kind of the basics. What do you need to know about a lease, and how do you develop a lease? Looking at the legal aspects, then moved into financial and tax implications, because some people were getting huge checks and they needed to know how to make sure to save enough money that they could pay their taxes. So there were some really basic things in terms of education that people needed. Then we moved into, around 2019, we started moving into renewable energy, because that was really coming on the scene, mostly in Northwest Ohio. A colleague in Van Wert County Extension was quite involved with that. Another one in Wyandotte County was involved with a large scale solar operation. So we moved into that particular area. The whole time though we were doing this, we were trying to approach it from a sustainability point of view, because shale oil and renewables have an impact on a community that affects the social structure, it affects the environment, and it affects the economy. So all three of those needed to be looked at, prepared for, and dealt with. So again, utility, wind and solar, we were looking at leasing issues, project siting considerations, and community planning. We actually developed a program that helped community leaders understand what the utilities were looking for, what the developers were looking for when they made their project siting considerations. Another project we offer, and still going on, both of these are going on, was working with individual farmers to help them understand if it was feasible and had a good return on their investment if they went solar in their operations. And we've reached about 1,100 participants through that program, and that's still ongoing. So this is kind of our team. We have an outreach and education initiatives or team, I should say, which includes extension educators, people from Farm Bureau, from ODNR, oil and gas, university researchers. A number of people involved with this symposium are members of this organization, and we've become a really good sounding board, sharing information. So that's been very effective. We've been meeting since about, 2008 or so, and have quite a bit of history in terms of what's happening in our communities. One of the other things we did too was looking at research on public pushback, because people have talked about pushback, and coming up with what we felt from our experience were the important things to do in a community if this kind of energy development was coming. And the first thing was early inclusive community engagement. To not kind of sneak into the courthouse to look for leases, but to be upfront and address the community's issues. And this is on the developers' part, as well as the community becoming engaged in that education, so they knew what to expect. So it was also very inclusive, inviting all the parties we possibly needed to invite who might be affected by this. we also talked to the industry about who they sent, because who they sent was almost as important as what they said when they reached out to communities. And what I mean by that is they were often sending people who did not have soft skills or facilitation skills. So we work with them to make sure that they knew, look, you know, these are human beings. You need to understand the local culture. You need to understand what's happening in this community before you can really develop any relationship. Neutral parties such as Extension could be a trusted educator. And then finally, one size does not fit all in terms of engaging communities and working on these projects. So that's basically what I wanted to share. I also want to mention a caution, which is energy transitions hurt communities, can hurt communities. So we need to be aware of that and support them any way we can, and be aware up front that these might possibly be things that will affect them negatively and affect individuals and communities. So that's that's my ending comment.
Great, thanks, Myra. Jeffrey has reappeared. Take it away.
Okay, we could try it again. We'll see how it goes. Like my worst fear coming true. See if I could share my screen again. Not sure how much we made it last time, but yeah, just wanted to mention that a lot of wind turbines in our future, if we want to make this transition feasible. And with 60,000 wind turbines right now, they're not evenly dispersed. You know, they are actually, in fact, quite concentrated in a few areas of the United States. Wanted to sort of zoom in on part of Illinois and Indiana here for our purposes. As you get closer, zoom in this area like North Lafayette, and you start to really see the scope of these wind turbines, that the concentration. And what's interesting is as we continue to increase the number of wind turbines, and you would think that they would branch out into new places, virgin territory that has yet to see wind development, but in a lot of cases they're sort of doubling down on places where it's already been put in, and it makes a lot of sense from a lot of different perspectives, including, you know, the transmission lines are there, the infrastructure is there, the leases with the landowners, which is a huge component, are already in place. The communities have already signed on and agreed to these wind farms, so that's, you know, part of the story there. But you can just sort of keep zooming in on the USGS database, and you can see, you know, that these are, you know, serious endeavors for places where these are located. And I think, you know, as you drive down the highway, may not sort of get the scope of sort of the ramifications for some of these places. I think this is the elementary school in that area. You just sort of see, you know, all the wind turbines in the distance. This, you know, this area of Indiana has turned out to be quite controversial. And a lot of people sort of point to it as a poster child for wind energy, not necessarily in a good way. And sort of the diagram in the middle just sort of is, you see this a lot in sort of people who are opponents of wind energy. And when we talk about sort of energy justice and like the equal distribution of energy impacts, you see this sort of diagram where, you know, there's one property owner who's receiving the majority of the benefits, and you have another property owner who's actually bearing the majority of the costs and not receiving much of the benefit there. And I mean, even if you just think about these places and like the population distribution, the vast majority of the people are going to be like living in the towns, in the small communities, and the number of landowners will be a relatively small percentage, just from that perspective. And then even amongst those landowners, you sort of have people who may be getting royalties and people who don't. And so this part, as I mentioned, this part of Indiana, and I guess Indiana as a whole has seen quite a bit of pushback to wind energy. You see just some of the, some of the, I guess, local discourse, you might say, around this issue. It's a local town council meeting where they had proposed a new wind farm, sort of like north, I guess it would be sort of north east of sort of that area that I highlighted. And there's a number of wind farms that were proposed in Indiana and have now been sort of postponed or have actually been sort of taken off the table due to sort of local opposition. And as I had mentioned earlier in the day, we talk about the just transition and sort of justice and environmental justice. There's actually, a lot of different domains related to justice. Two I wanted to highlight here, just the idea of procedural justice and recognition justice. And procedural justice being fairness and equity in decision-making, and recognitional justice is fairness and equity in who is recognized. And, I think a lot of the research, the preponderance of research looking at sort of local planning and zoning decisions, not just about energy, but about all sorts of different topics, finds that these are, extremely important in garnering sort of local support for some sort of planning or development or, change at a local level. Do people feel like they had a role in the decision-making? Do they feel like their voices were heard? Do they feel like their concerns were recognized? And, a lot of research has shown that people care more about that than they actually care about the outcome, and that they will accept, sort of an outcome that they are, less than thrilled about if they feel like they had a fair shake in the decision-making process. And I didn't really think I had too much time to sort of go into the ownership models for community energy and sort of wind energy, but the vast majority of wind turbines in the United States are sort of corporately owned. And a lot of that has to do with the production tax credit, which sort of the federal policy that's been driving a lot of this energy development. Basically, you can take a percent of the electricity that you produce and sort of offset your tax burden. And so the way that's sort of set up is, in order to benefit from that, you need to have a large tax burden. And the only sort of entities that are going to have a tax burden that's sort of worth this offset are sort of large corporate entities. And so if you think about that system, you immediately take out nonprofits. You immediately, take out educational institutions. You take, just sort of any sort of, if you're not generating profit, then you're not going to be able to take advantage of the production tax credit. One way sort of around that, especially with like energy cooperatives, they'll partner with a corporate partner and then sort of arrange a partnership where the corporate partner gets the tax credit in exchange for sort of building the turbines for the nonprofit entity. But that's, it's complicated, it's difficult, it's not that common. When in fact, most of it ends up being corporately owned. One alternative to this is sort of a local community owned, where the actual, community actually owns the infrastructure and is actually sort of directly getting the benefit from it. And as you might imagine, this type of ownership structure tends to be more positively received in the community. Sort of, in this bit of research, at least a lot more people sort of feeling neutral or positive about it, with less sort of like vehement opposition. So yeah, here's just one of the, I think there's 2 or 3 Indiana wind farms that have sort of been taken off the table in the last couple of years. And I think it's important to sort of point out that wind farm construction does have significant impacts to the community. Not only the construction activity, but also just sort of the land disturbance. I think in Ohio, oftentimes we think about it in terms of agricultural land, which I think wind energy is almost best suited for. But there's also a lot of other sort of contexts, thinking about out west where the land is sort of permanently scarred, thinking about like mountaintops and ridge tops where it's forested and you have to remove the trees to put in these wind turbines. And also, the the sort of greenhouse gas emissions from wind turbine production is not insignificant. And I think this is another area where it's sort of less well known what the true sort of life cycle impacts of these are. And then finally, one thing I wanted to point out is the disposal of these things. So we have sort of a problem in planning and engineering where we like to think of things that we're building as permanent. This includes, coal-fired power plants that were built in the 50s and 60s. The thought was basically, well, these things will just always be here, and but in fact they're closing now. And the same thing with these solar panels and these wind turbines. They say the average life expectancy of these are around 30 years, but that means half of them won't make it to 30 years. A lot of these, turbine blades crack, have to be replaced. It's sort of, common in wind farms. And there's really, as it stands right now, no way to recycle them. And so basically the only choice at this point is to put them in the landfill, which I think one of the biggest landfills that are accepting these now is in Wyoming. And so that's sort of becoming a community development strategy of accepting wind turbine waste. But that, also opens up a whole nother range of issues when it comes to sort of, environmental justice and these sort of range of impacts. So, don't think of these things as permanent, think of these things as just lasting 15, 20 years, at least with the current technology. And we have 200,000 more that we need to put in, at least, to sort of reach these modest climate goals. So I guess with that, I will stop and turn it over to Jeff.
Great, thanks, Jeffrey and Myra. It's clear that we have an enormous need to transition away from the ways in which we've done things. We also have enormous opportunities in doing that. And as we've highlighted, a number of enormous challenges. On one of the questions that I think we might want to engage with is from your perspectives on while there are challenges both with wind, solar, natural gas, coal, and so on, and issues, on balance, how do you see these different energy approaches affecting people and communities? And if you were to rank order or preference rank from your perspective, what would be the better paths? How would you do that?
I would take a stab at that by just saying, man, it sure is complicated. Solar panels also have these disposal issues. Solar sort of conflicts with agriculture, whereas with wind energy, it's sort of more, conducive. But, and it sort of depends on what the outcomes are. Are we talking employment? Are we talking, electricity production? Like, what are the things that were, community acceptance, revenues to communities? Like, what are the things that are most important? One thing I would say that seems like almost a no-brainer is this idea of distributed generation and putting production in a lot of little places as opposed to just a whole bunch of it in one big place.
Yeah, go ahead.
Either way is fine. You can go first if you like.
Okay, I was going to just weigh in real quickly and say, I just had this thought, if I was going to have one of these in my backyard, which would I like it to be? And I'm not sure I can answer that, but I think it's going to take a balance. It's going to take all of these energy sources. I would love to see us transition from fossil fuels completely out of that into renewable energy, but I don't think it's going to happen for some time yet. I think part of the equation is, are we going to reduce our consumption as a society, consumption of energy? And if we aren't reducing it and we keep increasing it, then we obviously need to have a myriad of sources of energy. So I guess I see them all being necessary, with hopefully transitioning into less fossil fuel.
Yeah, I would definitely agree with that. Different technologies, different renewable technologies are going to make sense in different environmental contexts, of course, and also in different social contexts. In some places, there are some things that just don't make sense, either because of a biogeophysical limitation or because of the way the social system is set up and what people want to accept and take ownership over and what they don't. I see and hope and pray that fossil fuels are on their way out and on their way out soon. And I say that not just as a researcher and an informed citizen, but as a parent who has kids who I want to have a viable life and a viable climate to live in. Just today, I got an article that I haven't had time to evaluate yet, but said that in 2018, when this research was conducted, an estimated 8 million people died as a result of the fossil fuel industry. That is a huge number. That's higher than previously estimated. And the previously estimated numbers were huge, right? This can't go on, right, on a year-to-year basis. And it also can't go on a generation-to-generation basis. So I think we need to do everything we can. I think we need to push in every possible way to make sure we do overcome our society's fossil fuel addictions. And key to that are some of the things that I was talking about, right? These ideas of shifting our values. This is monumental. This is a radical cultural paradigm shift that we need. And I don't know how to bring it about. I can't snap my fingers and make it happen. But more than anything, we need to realize that we can use less. We can promote efficiency. We don't all need to have giant houses and giant cars and independent vehicles and all of the other things that we are told our needs, but are actually not. We can live large on much, much less. You're muted.
It was great. I got that same study that you just referenced in my inbox 2.5 hours ago about fossil fuel pollution killed 8.7 million people in 2018. Yeah, so I think, part of, as we're wrapping up today, thank you all for your comments and your contributions and participation. I think as we're wrapping up, one question that comes up, and as we start to move into tomorrow, are we letting the realistic get in the way of the needed? We have a lot of challenges that we need to confront and address from the environmental perspective, the social perspective, the economic perspective, and they're all intertwined. And we need to address them now, and we need to move past the way we've done things in the past and envision quite a different future. And part of the question is, how do we get there? We are out of time. Tomorrow at 1 o'clock, we will kick back off with a brief recap of today, and then we will get into another keynote by Scott Tinker, who, as I mentioned earlier today, is among many contributions, has produced a couple documentaries, Switch and more recently Switch On, about the needed energy transition. So again, I thank you all for joining us. I thank all the panelists for lending their time today, and tomorrow we'll have a number more Ohio State faculty members and staff contributing to a discussion about buildings, a discussion about mobility, and discussion about what Ohio State is doing more specifically. So until tomorrow, I hope you all have a safe and nice evening, and I will we'll see you tomorrow. Thank you.
Thanks, Jeff.